Hello and welcome everyone on the conference between business and tech, episode 1, Microservices. My name is Tomasz Bogus. I'm from Scalac. And so let's get started. A little bit about Scalac. So Scalac is a software engineering consultancy company. We are doing trainings, custom software development. We are focused on functional programming, especially Scala. Since 2014, we are serving clients all over the world. 7 years on the market, 120 people and growing. This is a photo from our HQ in Gdańsk, Poland, from where I'm broadcasting right now. Let's get started with the question. When was actually the last time you visited your bank? I can tell you that you are visiting your bank almost every day, because you are no longer driving downtown to go to the bank and counter to do some stuff like do wires, check your balance, but you are doing this through the mobile app. So what I'm trying to point is that your experience through the online application is the experience how you see your bank. The recent COVID pandemic pushed the last contenders and the late majority towards digital transformation. For many, it's the only chance to save their businesses. Will every company be a software company at some point? I think we see this happening already. No matter what industry you are in, the business success now depends on your company's ability to build digital services and software more quickly and with higher quality, and to deliver those applications and services reliably at scale. I'm from business team and I talked to the customers over the last couple of years, and what I found is that what we are facing we were facing similar challenges where we are trying to drive business agility or respond to digital disruption. But we have this legacy old technology estate that's largely holding us back. When we hear modern application, we tend to discuss cloud technologies. And then we can feel very far away when you have this old legacy technology with a big tech debt. Regarding the Gartner, 2 out of 3 business leaders believe that they must pick up the pace of digitalization to remain competitive. It's more than 60%. What are the key factors that you should focus building your system, building your application? First of all is scalability. So let's imagine that you have a Black Friday or Cyber Monday and you are losing business because your system is not able to serve new customers. Your marketing did a great job, sent a lot of traffic to your website, but your system is not able to serve these clients. Scalability is very crucial. With an old legacy system, it's a big challenge to make it working. I guess that every SaaS business can't afford for any downtime. So this is another factor that you should consider building your modern application. How many times new clients asking you when the new feature will be available on your app because your competitor has this new feature? So releasing new features is really crucial to be on the competitive edge. And the very important factor is user experience. As you've seen on this page with this woman doing some mobile, I think that user experience based on data that is available for any product manager, for any team members to make improvements in your application based on data is really crucial for you and for your business, for your customers. And today we invited a lot of great speakers from all over the world, our friends, our clients, to tackle a new, maybe not a new, but for many companies, a new topic like microservices and how microservices can help you innovate in your business. I'm very happy that today we will have a chance to talk, to discuss. During each presentation, you will have a chance to ask the question. Please type your questions in the window chat, and we will ask these questions speakers just after each presentation. I guess that we are ready to start our first talk. I'm waiting just for Zuka Kakabadze, CEO of Fugo AI. Hello, Zuka. You are muted. Okay.
Thank you. Hi, Tomasz. Thank you.
Hello. So here with us is Zuka Kakabadze, CEO of Fugo AI, and he will be talking about very interesting thing especially for the technical point of view, how startups at the very early stage can embrace microservices. Welcome, Zuka. Handing over to you.
Thank you. Let me share my presentation. Okay. Okay. Oops. Okay, thank you very much, Tomasz, for the introduction. So, as a startup, when you're building a software product from scratch, the initial architectural decision you make will have long-lasting consequences. It's similar to building the foundations for a house. The wrong decision can come back and bite, hinder, or even break your startup. Hi, my name is Zuka. I'm the founder and the CTO of Fugo. And today I'm going to tell you about our journey as a SaaS startup and some of the key architectural decisions we made to get to where we are now. I believe the problems we encountered are true not only for startups, but any greenfield software project. To understand the decisions we made as a startup, you first have to understand the problem we set out to solve. 1 in 2 screens sold today end up not in people's living rooms, but in businesses like cafes, shops, and hotels. But the vast majority are not connected to a software and are managed manually using USB sticks or other DIY solutions. As a result, these lazy screens end up showing irrelevant and outdated content and sometimes showing nothing at all. This is why we decided to build Fugo. Fugo is a digital signage content management software that allows businesses to create, publish, monitor, and measure audience engagement. At Fugo, our goal is to turn lazy screens into smart connected devices. Digital signage is an important part of any business, especially the customer-facing ones. It's a face of a company, and some businesses own hundreds or even thousands of screens in their network. So the responsibility you have there can be huge. Your system has to be strong and stable, because if it goes down, we can end up with a scene similar to the one we saw unravel at Gatwick Airport back in 2018, when flights had to be delayed for days because of a failure in their digital signage system. We already knew the domain problem pretty well, but building an innovative product is a risky strategy. Our solution had to find its own market niche, and this required testing range of hypotheses about our users' needs and expectations by going through a rigorous build, measure, learn cycle. Once you find a repeatable business model, product market fit, you can then scale the product as fast as possible. Given the restrictions and business goals we had to make trade-offs when building our software. We summarized our main software goals into three main criteria. Quick time to market. In order to validate our business idea within the budget constraints, we needed to release Fugo and reach users quickly. Extensibility. We had to iterate and release features quickly to meet customers' changing demands. Easy future scalability to avoid replatforming our entire system in 4 to 5 years down the line. Of course, this last point is only applicable if you're successful. Today, instead of telling you all the theoretical arguments for and against microservice architecture that will be comprehensively discussed during this event, I'm sure, I wanted to tell you instead the journey Fugo went on and why we opted to use the latest tools of the trade to build a hybrid microservice architecture with the help of Scalac that is extensible, resilient, scalable, and fault-tolerant. Initially, I'm going to discuss Fugo's logical architecture and how we applied high-level functional architectural patterns to design a modular system. Then I will demonstrate how this looks in our code. And finally, I will show you how we mapped our logical design into a physical architecture, like microservices. So first and foremost, we wanted to align our software design goals with Fugo's business requirements. In fact, you might be surprised to hear that we didn't even discuss the idea of opting for monolith or microservice at the early stages. We simply wanted our logical architecture to be indifferent to the physical architecture. One of the goals of a good architecture is to define the various boundaries between containers, components, and modules such that when new requirements arise, as they will, the cost of change is minimized. With this in mind, we based our software design on functional architecture patterns. FP is well known for organizing code at the low level, but we can also apply FP principles to high-level design and architecture. This reduces complexity and improves the modularity of a system, whilst increasing testability and maintainability of an application. The good thing about functional architecture is that it automatically enforces high cohesion and low coupling without having to enforce team discipline. FP also gives you the ability to break down a problem into smaller, more manageable chunks that can be solved easily and then composed into a larger solution. The composition and abstraction gives you an ability to reuse your code and build new solutions from existing solutions. We will see examples of this throughout the presentation. One of the basic units of functional architecture, functional architecture is a workflow. By basic unit, I mean you can actually run an individual workflow if you want to into a standalone deployable container like they do in a microservice architecture. Workflows are built up using pure functions as independent units, containing only functionality they need. What's important is that workflows compose like functions do in a low level. From an architectural perspective, a workflow is a one-directional pipeline with inputs and outputs, as opposed to request response model in object-oriented approach. The workflows we implemented in Fugo generally have a similar structure. It receives a command as an input, makes a business decision, transforms the data, and then produces new event as an output. So initially, we prepared UX designs for our software, describing Fugo's domain and core functionalities that software had to have in order to solve our users' problems. The designs clearly outline must-haves, good-to-haves, and future features on very granular level. Why do we have such granularity? Well, we wanted to break down complexity and minimize the risk of change. For example, if we wanted to change the way uploading images works, it should not affect the way screens are paired. Every core feature from the UX design was translated into a workflow to kickstart our architectural design. As software engineers, our next task is to group these features or workflows into logical units. We used domain-driven design, DDD, to group related workflows into bounded contexts. DDD creates a shared mental model and aligns business and tech teams so that everyone is using the same terminology and the same words. This model is also present in the code. So let's break down a little further why context and why bounded. Within the context, we share a common language and the design is coherent and unified. By bounded, we want to reduce coupling between subsystems so that they can evolve independently. Autonomy is crucial here. Having autonomy means that the bounded context can make decisions without needing to wait on decisions or information from other bounded contexts. And if one goes down, it can continue operating independently. In order to avoid too many cooks in the kitchen problem, a bounded context should be owned by a single team or a developer. But a single developer can own multiple bounded contexts. So how does this relate to a physical architecture? So if the entire system is implemented as a single monolith, a bounded context can be as simple as a separate modules within a single container. Alternatively, each bounded context can be deployed separately in its own container, like in a classic server-oriented architecture. Or we could go more fine-grained and make each individual flow into a standalone and deployable containers, like in a microservice architecture. At this early stage, however, we do not need to commit to a particular architecture. The translation from the logical design to the deployable equivalent is not critical, as long as we ensure that the bounded contexts stay decoupled and autonomous. This is a simplified version of how we initially divided Fugo into bounded contexts using DDD principles. As you can see, the billing bounded context is independent from the screen bounded context. Some features might require multiple workflows from different bounded contexts. In this case, communication is achieved using events. Workflows within a bounded context are triggered by events. And an event triggering a workflow is actually a logical view, not a physical one. And this actually can be implemented either using request-driven command and control, which increases coupling, or event-driven queue using queues and message buses that decreases coupling, or a bit of both, like a hybrid version. If bounded contexts are not correctly created, you'll eventually you eventually turn your nicely decoupled architecture into a big bowl of mud. So how is code structured within the bounded context? The natural intuition is to use the traditional layered approach, where workflows basically go through every layer. This approach is problematic because any change in the workflow propagates to other layers and workflows. This architecture significantly reduces our ability to extend and iterate Fuga. Instead, we inverted dependencies and made it point inwards, following the functional onion architecture style. This way, the infrastructure code knows the core domain, but not the other way around. And I/O is kept at the edges. The domain entails just pure logic and is isolated from the infrastructure. For example, a function that interacts with database is impure and therefore will not exist in the domain. But the core domain consists of abstract data types and pure functions that operate on these abstract data types. Types can be used to represent the domain in a fine-grained, self-documenting way. In many cases, types can even be used to encode business rules so that you literally cannot create incorrect code. You can then use the static type checking almost as an instant unit test, making sure that your code is correct at compile time. And this approach can actually increase your time to market, but it improves the reliability of your code, and any future changes can be rolled out with fewer tests and with greater confidence and speed. This is an example of what a workflow looks like in Fugo. We wanted our code to represent a pipeline. For example, when you publish Fugo playlist, the flow goes as follows. Get a playlist from a repository, send an event that says playlist is published, log that the playlist is published, and return the playlist. In our code, we have a function for each step. Each step needs to be stateless and without side effects so that it can be tested and reasoned independently. However, in practice, chaining functions into workflows is harder than it looks because the output of the one function does not match the input of the next function in the pipeline. And there are two reasons for this. The first is that functions have dependencies and extra parameters that are not part of the workflow pipeline. And the second is that they also have effects such as errors. And up until recently, actually, building such an architecture was unimaginable in a startup and required a considerable amount of acrobatics to achieve this. In order to build functional architecture, you need functional programming language. And that's why we decided to go for Scala ecosystem and Zio. We were attracted to using Scala because it is a powerful and expressive language with a strong type system. It allows us to reuse existing GVM infrastructure, which is important for startups as time to market is very short. And its concurrent and parallel programming tools allows for better utilization of the server resources, and as a result, smaller AWS bill. We combine this with Zio because it has a reusable and composable abstractions, and it gives us the ability to apply functional programming to our high-level design and architecture, and works surprisingly well with existing Scala and Java frameworks and libraries. It automatically makes the code base consistent and forces our developers to stick to FP, whereas other methods requires some team discipline. And one thing startups can lack is discipline. This is what our published playlist workflow looks like in Zio. Zio library is centered around Zio type. Zio instance here describes effects that take an input and produces either an error or a desired value. So as you can see, Zio has three argument types. The input type R, which is an environment or a dependency. Output type E, which is an error. And in value type, which is your successful value. The publish playlist function sequentially composes all the sub-functions using for comprehension. The sub-functions themselves are zero types as well. And if successful, the publish playlist function returns a playlist. If there is a failure at any stage in the pipeline, it produces a playlist error type describing the error. This function doesn't actually run. It is just a description of a workflow. To run it, you need to provide the dependencies. You can create dependencies in Zio using Z-layers, and Z-layers allows you to create services that then can be composed to build a graph of dependencies. The example above shows a playlist queue service API that lives in our domain layer. And below that is an SQS implementation of the playlist queue service. And this lives in an infrastructure layer. The graphs can then be injected into modules to make Zio workflow runnable. For each bounded context, we then construct dependency graph and inject them into our Scala module, like shown in here. These modules are either run as separate microservices or as a modular monolith. And in a modular monolith, Z-layers actually allows you to share dependencies across modules to save resources. For example, an HTTP client pool. In order to run our publish playlist workflow, you need to provide the layer graph as shown here. So after completing our logical architecture, we need to consider technical requirements and map logical architecture to a physical one. Each Fugo bounded context or module has different requirements in terms of scaling, availability, or behavior. Currently, we have 8 microservices running on AWS infrastructure and one modular monolith called Fugo CMS. Fugo CMS is deployed as a modular monolith because initially it was not clear which workflow would require scaling. Each module in the monolith has its own DynamoDB table and SQS queue that can scale with the module if we want to. We put them in a monolith because microservices can have operational overhead, but you can actually mitigate this by automating the infrastructure and using cloud services to their fullest extent, like using infrastructure as a code, Kubernetes or Fargate in our case. And this allows you to then concentrate on the business code and spend less time on the infrastructure code. On the other hand, we knew that the router module, for example, that coordinates screens, needs to be a singleton and be deployed as a separate microservice. And the separation between the Fugo CMS and the router was obvious because they have a completely different scaling requirements. And we don't want the performance of router to affect our user experience, and we don't want Fugo CMS to affect the screen functionalities. So monolith or microservice, what should you choose? Well, it's not a black and white choice. It is more a spectrum, which you can consistently shift if you use the logical architecture that we presented here. And as mentioned, one point in favor of using workflows as the unit of design is that they can be physically deployed in any number of ways. For example, as a modular monolith, a microservice, or even as an independent serverless function. So ultimately, the decision has to come from your use case. But either way, I would strongly recommend using a functional workflow architecture, as it gives you a lot of flexibility whether you want to run your system either as a monolith initially and then shift towards microservice, or if you want to deploy microservice straight away. Well, that was our Fugos journey. Thank you so much. And if you have any questions, I'll be happy to take.
Thank you very much, Zuka.
Thank you.
Thank you. Yeah, I'm trying maybe because we are waiting for questions from the main chat, but let me ask this question because you can still name your company as a startup, as I understand. So do you think that having this approach at the very early stage gives you more advantage competing with your with your colleagues from the other startups? Or because when I'm talking with startups, they are trying to build something as fast as possible, as quickly as possible, to just prove product market fit. Your approach is a little bit different. Your focus, because you are from the engineering field. So do you think that this makes competitive advantage, this approach that you use in your startup?
Yeah, thank you, Tomasz. It's an interesting question. I think we have to define at what stage startup is, and what sort of resources they have. I mean, if they're at the very, very early stage and they're just like very limited budget and they just want to try something out, maybe you might not even sit down and spend any time on architecting anything. But if you maybe like raise your seed funding and you want to like build a product, I believe today's frameworks, programming languages, and infrastructure automation tools allows you to spin up really high quality systems that you don't need to rewrite in the future. So you do need to have some certain level of expertise, and I guess that's when you guys come in. If a startup lacks a certain a certain scale, then it's a good example for Scalac to step in and guide that, because eventually the benefits down the line are very clear. And for me, for example, for our case, what we noticed was that having a high quality product from the get-go was very important. This gave us confidence to speak to not only small clients but big clients as well, and sell them our service. And we knew that our product is not bullshit, it's not going to break. So I think it does give you an advantage.
Okay. We have one question, as I see from our audience. It's a technical one. Hi, workflows are Zio specific approach? This is the question.
No, it's not. It's functional programming specific, but we applied, we used Zio to implement them. Before, it was quite hard to use workflows in a different programming language, or using you needed a lot of functional programming skill and training, but Zio allows you to apply build workflows without even kind of understanding functional programming, or you don't even need to be an expert in functional programming. So
okay, thank you very much. Okay, that's all of the questions. So, okay, another one. Okay, waiting for the question. Okay, let me read it. So that was a great explanation of all the constraints in your designs. And we see the question. I will be interested in more details about techniques for building a modular monolith.
So, as I explained, we initially split up our system into bounded contexts. And then we deployed these modules as a single in a single container. And if you're familiar with Scala, that you can do using SBT. And then in the future, if we find that one of the modules requires scaling because the usage is going up, then we can very easily just change some code in Terraform and dissect our modular monolith and separate it into a separate container. I mean, if you want to kind of go into more details, I'm happy to. I will share my contact details after the presentation, and I'm happy to discuss it as well.
Thank you very much. We will follow up if the question will be need more explanation. Okay, so thank you very much, Zuka, for your time. It was
Thank
a
you.
pleasure having you today. All the best with your venture.
Thank
and
you.
within the next talk, we'll start in. Okay, there's one more question I see. Let me. Okay. Okay, we have it. What would be the difference between using Zio and using the Lightbend microservices tooling, such as Lagoon?
Yeah. I don't really have much experience with Lagom, but I believe Lagom is based on Akka technology and Actor systems. So as I understand, Zio is more functional. It uses more functional programming principles. And yeah, I think they're both good. The one thing that I can say that Lagom is probably quite good with when it comes to distribution, but I don't know. It's I don't think they're even comparable, because one is more like a framework, and yeah, I don't have much experience with Lagom, so.
Okay. In a couple of hours, we will have a speaker from Lightbend, so maybe we can discuss also this later. Yeah, so then thank you once more, Zuka, for your time. The next talk about how to secure microservices will start in 12 minutes. So yeah, so let's wait for the next talk just a couple of minutes, and we will get back online soon. Hello and welcome on our conference about microservices. We are going to start our next talk in a minute. Please subscribe our channel to have recent videos, recent posts on our social media, scalac.io, if you would like to be updated with any news from Scala and technology world. So during every session, please ask questions on the chat you have in the window next to the video, and the questions will be asked after the talk to keep time. And so we are waiting for our next speaker. I would like to introduce our next speaker, Łukasz Marchewka, consultant from Scalac, and he will be talking about a very interesting and important topic like security and microservices. Welcome, Łukasz, and take it away.
Hello, can you hear me? Oh, yes. Okay, so today we are going to talk how to secure microservices. My name is Łukasz Marchewka. I'm coding software architect working for Scala C. I'm a huge fan of functional programming, domain-driven design, and Scala. So the question is why you have to secure our microservices. And I think it's the best reason why you have to care about that. But what exactly is a cyber incident? So as you can see, cyber incident might have many different forms. One of them might be quite expensive, like Yahoo, over $300 million, but also some of them might be not so much painful, but might be quite common. So the next question is how we can secure microservices. So, and you should be aware there is no universal model, no universal design which you can apply, but each time you have to take into account a few factors, like risk, of your business, needs of your business, and also type of your business. After that, cost of cyber incident, and also cost of implementation. And after that, also time to market. So in practice, we don't have infinite resources like time and money. So each time we have to base on some trust. And what is exactly trust, I'm going to explain later. So today we are going to talk about factors which should take into account to building your security design, a few common mistakes. Also, I'm going to demonstrate a few different approaches, solution with pros and cons, and components which you can use to implement that solution. So what exactly is security? Security is a very broad topic. Today we are going to talk only about authentication, authorization, encryption, and single sign-on. But this much more. So let's start. Before microservices, we had monolith. And monolith was quite easy because we have implemented everything in one place. So we have implemented business logic, we have implemented security, tracing, metrics, and everything was mixed together. And after that, we have decided to implement microservices. But very often, we implement microservices using the same pattern. So security, business logic, and everything else is mixed together in one application. And but how security is implemented? Security is implemented as code, as before, so as plugin, as middleware. And that approach has a few consequences. Like we have broken our single responsibility, so the reason why we have decided to create microservices. Also, each microservice might be implemented in different technology, different language, and then you have to use different libraries to implement your security. And of course, each of them might have different quality. After that, you have to maintain many different implementations. You have to patch them. And you have many different implementations in many different places. So after that, testing of that solution is quite painful because you can't verify one place if your application or like your product is secure, but you have to test each microservice. So, but it's not everything. After that, a user very often has to authenticate in one service, like here, and using the same session, the same token, have to send request another service. So after that, we have to implement sharing session between components, like and how we are doing. very often we just set up a new application. It might be distributed database, key value store like Redis, or different applications. And then all components with security communicate with that one central application. And of course, it has one consequence, because that traffic might be quite huge, and eventually you might have single point of failure, but also performance issue. Of course, we can reduce that pain by adding some availability, adding some replicas, caching, but still is something what we have to do. But that approach has one plus. It's quite easy. We can use exactly the same tooling as before for monolith. We don't need extra infrastructure, and we don't need extra specialists. And that model is probably implemented by your team if you don't have any DevOps, you don't have any security specialists, and architect. So let's try to simplify that. So let's focus. Let's start with communication between our microservices and that new server which we have created. And for that, we can use OpenID Connect, which is the very interesting protocol framework as API. But what exactly is OpenID? OpenID is a protocol when we can implement that authorization part. So user can authenticate to one server, so we have to set up new server, provide some credentials, and after that receive some token. So it's named exactly JSON Web Token, and that token is signed by authorization server. And after that, client store that token on their side. So we can compare that process to joining to new company. So when we start to work for new company, we have to go to proper department, sign some documents, show our ID, and after that we receive a card. That card is somehow signed by that department, and after that we don't have to authenticate, prove our identity anymore in other departments, but with that card we can open all doors which we can. So also that card has some kind of permission, what we can do. And the same here, that JSON Web Token has some scope, and that scope allows us to do something. And after that, when we want to do something with that our services, we have to send request to our services with that JSON Web Token, and we can execute operation on it. And but what else? Then our security have to only verify if the signature, exactly certificate, is still valid. And if it's valid and user has access to execute that operation, we can allow or reject the request. So that approach is very nice because we can reduce communication between our microservices and authorization server to minimum, because we don't have to verify each request, but we have to only verify if certificate is still valid every sometime, not for each request. But with microservices is a little difficult because we have many different microservices still, and still we have to implement the same pattern, the same security middleware plugin, something like that, in many different applications. And so we have solved problem with single point of failure, we have solved problem with performance issue, but still we have a few other problems to solve. So, but we have introduced a new component. So let's verify what we can do with that new component. So, and of course, you shouldn't implement that component yourself. We can use something like it's named as identity provider, and there's many different implementation. I think each cloud provider provides their own identity provider. But what exactly is identity provider? Identity provider is a service. You don't have to implement it yourself, just install and configure. And identity provider provides some functionality which is quite common, like user registration, integration with social medias. We can, for example, integrate our identity provider with Active Directory, LDAP. We can implement single sign-on stuff, and also multi-factor. And also, they provide very nice UI, some management tool to manage user, manage clients, and so on. And some of them also provides login page, which you can customize a little. Some of them much more than a little, and use that login page in our application. So even though we don't have to implement login page anymore. So With identity provider, we can simplify, so we can just don't have to implement, we can just use that component. So we have simplified our application. But it's not everything. So let's focus on those components. So we have to implement security everywhere. But why is so important? I think we have at least 4 reasons why we can simplify, or why we should simplify. So how we can do that? We can use API Gateway, and API Gateway is also a service which you can install, configure, and also almost each cloud provider provide their own implementation. So yes, so we can just use, and we should use exactly that API Gateway. Don't implement it yourself. But what exactly is API Gateway? API Gateway is a component service which implements a few the most common patterns for microservices. Like each time you have to implement authorization, floating quotes, secure caches, and so on. So instead of implement it ourselves again and again, and for many different technologies and so on, we can implement, exactly not implement, enable and configure on API Gateway level. And as you can see, API Gateway provides many different functionalities. So it's definitely worth using, and especially for microservices. So how we can use API Gateway in our solution? So we can put API Gateway between clients and our microservices, and then move security from microservices to API Gateway, and then configure the security with our IDP. So after that, we have solved at least 4 problems which we had until now. But of course, each solution has some consequences, like we have introduced extra infrastructure. But we can achieve something more. On the left side, we are not able to secure our product from in one central place. So each time we have to rely on the development team to implement security correctly. But on the right side, we can implement, configure exactly security in one central place. And the on communication with our microservices will go through the API Gateway. So there is no option to execute our API Gateway and skip security. And it's quite interesting because, for example, some time ago, I have reviewed another company which haven't used API Gateway at that point. And they were surprised that some services, exactly all of them, was exactly publicly available, because one team thought that security is implemented on in microservices, and but the rest of the team haven't been aware that there is no global policy to protect that. So with API Gateway, we can be sure that our services are secure, and now we can only explicitly disable security only for some operation, for public operation. So, but okay, so let's go deeper into API Gateway. Well, what we can do. So we have configured our microservices API Gateway with some security, and after that we should create some firewall around our microservices. So there's only one entry point to our microservices through API Gateway. And after that, that approach is named Trust the Network. Why? Because in that situation, intruder wouldn't be able to communicate with our microservices outside the network because we have firewall. But if intruder will be able to get access to our network, then they have access to everything exactly. So it's exactly the name. We trust our network. So in practice, we are adding more security for our microservices because we want to be secure. And that solution, of course, is not the trust and the network anymore, and it has some consequences. Exactly consequences inherited from both two previous solutions. Like we have extra infrastructure, API Gateway level, API Gateway, plus we have extra security, many different technologies, many different places, broken security responsibility. But it's not everything. So, of course, our application is more secure now, but it's not everything. So, in practice, we have to, so we receive some, let's say, JSON Web Token, and after that, we forward that JSON Web Token to our microservices. And after that, we have to also implement communication between microservices, like here. And of course, if we can, we should forward JSON Web Token to another microservices, so we are safe. But in practice, we have to implement async operation, cron jobs, execute operation on someone else. And in that situation, we can forward JSON Web Token. Why? Because each JSON Web Token has some expiration date. So after that, the token might be rejected. So what we are doing in practice, we very often just create another endpoint, which is unsecure, and implement unsecure communication between microservices. Why? Because it's easier. And of course, that approach is quite unsafe. It's very unsafe because we have illusion that we have a secure application, but in practice, we have some endpoints which are unsecure and we don't know. So it's very, very risky, exactly. Okay, but let's talk about encryption. So until now, we have deal only with security. But now, what is encryption? So we have two services. Of course, both of them are secure. We are, for example, using JSON Web Token with some signature. But we don't have encryption. So what it means? We have intruder, which can spy us. So because that communication is unencrypted. So it's just plain text which they can read. So what we can do? We should introduce TLS, so transport layer security, which will encrypt communication between our microservices, and in that situation, intruder wouldn't be able to spy us. But in practice, we use API gateway or load balancer. Very often we use load balancer, API gateway, not each time, but load balancer almost always. And we implement something like SSL termination. And it means that we have encryption between client to API gateway, but from API gateway to our services, we don't have encryption. So with our approach, the previous approach, we have encryption to API gateway level, so from client to our cloud. But after that, in our network, we might decide to implement security, extra security, we might use that security. But without encryption, they can spy us. They can't execute requests, but they can spy us. So what we can do? We can add another TLS inside our network. And now our services are secure because of that extra security. And also we have encryption inside our network. So, but why we have to implement so many security? So we have on the API gateway, we have also security for our microservices, and we know it's painful. So, and the reason is inter-service communication. So let's go deeper into inter-service communication to understand what we can do. So we have two services, they are encrypted. And very often it's encrypted, so communication is encrypted, we know about that. And we also have security, and very often implemented as a code. And exactly that piece of the application is painful because we have many different implementations, many different technologies. Yes, so what we can do? So, and maybe you can just remove security. We have TLS, so why we need security? TLS is not enough because TLS just encrypt communication between services. And in that situation, intruder will be able to send requests to us and fetch data, modify data. Of course, that communication between intruder and our service will be encrypted, but that person can still execute requests, what is definitely wrong. So we can remove. But let's go deeper a little into TLS. So TLS is mostly about encryption. So maybe we can do something else to solve our issue. So we can introduce mutual TLS. So mutual TLS is also TLS. So we have encryption before. But with mutual TLS, our services have trusted. And only services which are trusted, so have proper certificate in the trustor, can send requests to us, and everything else will be rejected. So in our case, we don't have to implement extra security as a code, but we can introduce MTLS, and it is enough to prevent situation where intruder will be able to send requests to us. So in the previous solution, we can introduce MTLS, and now intruder wouldn't be able to spy us, and also wouldn't be able to send requests to us. So, but how we can do that? So we don't want to implement security as code, but still we want to implement MTLS. So what is different between MTLS and JSON Web Token? And the question is not what is the difference, but how we can solve that issue. So very often we just implement, create some Kubernetes pod or something like that, and we run application with some implementation of security. But let's do something else. Let's create another application on the same pod, so on this another container, and move security there. Of course, there might be also the JSON Web Token, So, and now let's only open that proxy for the incoming communication. So application should be just closed, and user shouldn't be able to send requests to our application. But now we can just configure MTLS on proxy level, so they can send requests to us to proxy, and we have communication to proxy. But now we don't have encrypted communication between proxy and application because we don't need. So application becomes simpler. And the same with sending requests outside. So we can send requests from app to proxy, and then proxy will send encrypted requests with MTLS to somewhere else. And but it sounds to be quite complex. So we have to implement proxy, we have to configure proxy, and this is something new we haven't done before. So what we can do? And again, we shouldn't implement. We should use existing technology, and they service mesh. What is a very nice approach, very nice pattern which you can use. And again, there's many different implementations. Don't implement it again, but use one of them. But what exactly is service mesh? Service mesh is a set of patterns. So like service mesh is a pattern to simplify communication service to service, and all of them provide secure communication between service and service. And very often using MTLS. I think always MTLS. Also, for free, they have load balancer, security discovery. Also, you can enable tracing on the proxy level. And now we don't have to implement tracing anymore in our services. The same retries, timeouts, and so on. So with security mesh, we can just simplify our application because we don't have to implement that technology-related stuff in our business logic, in our microservices, but we can focus on our goal exactly, to implement business logic, domain logic, not everything around. So with everything what we have discussed now, we can just simplify our application. So as you can see, our application become quite easy. We don't have to implement security, even though we don't have to implement tracing anymore. But we have to introduce 2 new components, actually 3, 4 new components. So API gateway, MTLS, service mesh, and IDP. But the question is, can we trust other services? Very often yes, but sometimes not. But what is consequence? So let's assume we have a situation where client can send request to our service A, and of course we have MTLS between service A and service B. So client sends some request using JSON token with some permission, its name scope. So what user can do with that token. And after that, we might forward this. So from service A, we can send a request to service B with the same permission. And that request should be accepted. But let's assume service A is broken, and now that permission has been changed. So instead of read, we have run. And now we are not able to verify if request is valid or not. So in that situation, request also will be accepted, what is definitely wrong. So what we can do, so instead of that, we can also forward our JSON token to other services. And now with valid JSON token will be accepted. But with change, when JSON token is changed, for example, we have changed scope, then the signature is invalid and request will be rejected. So if you want to implement more secure solution, you can also add JSON token or something else. So that approach now is much more secure than before, but become quite complex. Not complex in our application. So from development point of view, it's quite easy, but we need extra infrastructure and quite complex infrastructure. So until now, we have discussed only about sync communication. And what with async communication? And when you decide to implement microservices, you should always prefer async communication than sync communication. So let's compare those 2 approaches. So with sync communication, we know how we can secure at MTLS or at least TLS, and maybe implement some security on the in our application. And what we can do with async communication? Of course, quite often we just implement security only on our consuming applications. So and Kafka is just an example here, because the same problem and the same solution you can implement for Kafka, SNS, RabbitMQ, and so on. So everywhere. So that pattern is universal, which we are going to discuss. So And very often we just implement something like that. But that approach has one consequence, because intruder can first send a lot of requests to our Kafka and then slow down consuming valid requests, but also can pull messages from Kafka, from RabbitMQ, what is definitely much worse. So what we can do, we can introduce MTLS between producer and consumer, and also secure Kafka using some access control list. And exactly that approach is recommended by Kafka, and it's only exactly so. Yes, so Kafka is secure in such way, but also you can do exactly the same stuff for, let's say, RabbitMQ. So let's compare sync communication and async communication. So async communication is about producing and pulling. So if you decide to use MTLS and secure our service, then as you can see, there's no huge difference between sync and async communication. Exactly the same, because async communication is, let's say, two sync communications. So if you implement the same protocol as for sync communication or async communication, it's exactly the same. So after that, we have secure communication between microservices, we have secure our network, but it's not everything. We have also secure our infrastructure, like databases, messaging platform, and so on. And in practice, we secure database quite often, but microservices, but Kafka, until now, I have seen secure Kafka only a few times. And and of course, it might be quite painful. So each time when you have a new component in your infrastructure, you should use TLS or even better MTLS. You should use username, password, some access control, roles, permission, and so on. But after that, data stored by those components are going somewhere. Exactly, they'll be stored on the hard drive. So also we should encrypt our data, our storage. So I have started that our solution based on some trust, and we have to decide what we trust. So of course we shouldn't trust our users, we shouldn't trust data, we shouldn't trust devices, network, and application. And after that, if we decide to don't trust nothing, then we can implement something what is named zero trust. And zero trust is the most advanced and nowadays the most sophisticated approach to secure application. So with the most secure approaches like zero trust, you can just secure your application very, very well. But in practice, so we don't have a lot of resources. So what is cost exactly? Cost is not only money, but also is time, is your knowledge, your experience. So in practice, it might be too expensive and also too painful exactly to introduce zero trust or the most sophisticated solution at the beginning. So maybe we can start something easier, and maybe trust the network is enough at the beginning because it's quite easy to introduce. And after that, we can add another resources to secure application later. So I have started that everything based on the trust, and the same here. So it's exactly reason why everything based on the trust. So what we have to decide what we trust, and based on that, we have to take into account some factors and design model which is useful and enough for us. And of course, with time, you can just improve it. But it's not everything. So also you have to secure much more components like Kafka, cloud provider. Also, sometimes you have to create trusted domains. You have to manage your certificate, and after that, provide certificates to your application. You have to store credentials somewhere and provide credentials to your services, and so on. So there's much more components to secure. So thank you for today.
Thank you very much, Łukasz, for your talk. I see that we have one question. I'm waiting for the other questions. If you would like to ask any question to Łukasz, the best way is to on the chat, and we can see it. Okay, the first question is, how about using HTTP server as API gateway? Nginx is popular choice for that problem.
Yes, Nginx is used quite often as API gateway, Of course, it wasn't designed as API gateway, but they have introduced some components to, for example, verify JSON to web token. So yes, we can. I personally prefer to use components created exactly created as API gateway, like even Kong or AWS API gateway. So you can use Nginx as API gateway, but it's, in my opinion, configuration not so easy. So I personally prefer other components, but I have seen a few projects using Nginx.
Okay, thank you, Łukasz. Do we have any more questions? Okay, no more for now. Maybe one question from my side. I'm from the business team. So regarding, because as I see, the entrance to the whole application is through this API gateway.
Yes.
In this solution. So what happened if something going wrong and API gateway is not working for some reasons? Is it a kind of single point of failure? Might be, or?
It might be, but when we decide to use cloud provider, they have provide high availability. And if we decide to deploy API gateway as our service, then we have to scale it and provide high availability ourselves. So it might be a single point of failure if you deploy only one instance of API gateway, but in practice, you should deploy at least 2, 3.
Okay, so we are secure. Okay.
Yeah, we are secure.
Thank you. No more questions. So thank you very much once more, Łukasz, for joining us. Of course, if you have any questions, you can, because Łukasz is from Scalac, so you can just maybe send a short message on info@scalac.io, and we can transfer any question to Łukasz later. Okay, so we, in just 4 minutes, start another talk. Grab your drinks and join us in 4 minutes. Thank you. Hello and welcome in our next session. And I would like to introduce our next speaker. And waiting for our next speaker. Okay. So I would like to introduce our next speaker, John DeGose, CEO of Zyverge. Welcome, John.
Thank you.
He will be talking about hype and hope of microservices. So handing over to you, John. Thank you.
Thank you, Thomas. All right, let me share my screen. Does this look good?
Yes, all is perfect. We can start.
All right, fantastic. Hello, everyone, and welcome to my talk today, The Hype and Hope of Microservices. So in this talk today, what I hope to do is give you a little bit of the big picture about microservices. First off, what are they and why are they important? What problem is it that microservices are solving? And then I'm going to talk about some of the day-to-day pains that you encounter as you go in to deploy maybe your first microservice architecture. Because even though microservices are in fact a solution to many real problems, nonetheless, they're not the simplest technology to deploy successfully at scale. And then finally, in the end, I'm going to talk a little bit about where microservices are going, what sorts of technologies exist out there to help make companies more successful when they attempt to go down the microservice architecture, and how that might change over time. And finally, I'm going to try to do all of this in 30 minutes, which is going to be a bit of a challenge because in this pandemic era, I've gotten used to giving 2-hour-long talks. Feel free to cut me off if I start running over. All right, hype. Where do microservices come from? Well, if you're not doing a microservice architecture, you're doing a so-called monolithic architecture. And monolithic architectures, they bundle all of the functionality required by an application into a single unit that exists together, it's packaged together, it's deployed together, it's run in production together. It is the monolith. It's the Ruby on Rails app. It is. We've all had these monoliths. We've all built them. We've all dealt with them. This was the way you used to build all applications. All applications were monoliths. And it's only really the edge of the application, the outside world, that interacts with the service directly. And then every other part of the application is just a bit of code. And so you have code calling other code and so forth. And there definitely are advantages to building a monolith. And one is it's just lower overhead. And that's because in a monolithic application, one part of the code simply directly calls another part of the code. There's nothing in between them. It's just ordinary code, all living together, possibly even in the same repository. So that reduces overhead and helps you move faster when it comes time to developing applications. However, we have learned from trial and error from many, many monoliths over probably 2 or 3 decades now that this style of architecture is fraught with serious drawbacks. And one of them is maintenance. So we go in and we need to change some part of our application like search, and we need to add new features or change the way it works a little bit. And then unfortunately, we have to go into all the other pieces of our application that are using that, and we have to change them at the same time. And of course, this is happening concurrently in parallel by all the developers who are working on the monolith. So if you've got 50 developers all changing one part of the application, they're all updating their part, but then they're updating all the other parts of the application at the same time. And that creates a maintenance nightmare because it could very well be that most of the other parts of the application, they don't need the new functionality. They don't really need to be updated right now. And having to update them is going to slow us down. It's going to add complication. It's going to extend the amount of time in which we're all sort of concurrently editing all of these different files and trying to make sense of them and doing pull requests and merging conflicts and all of that. Creates maintenance hell. And not just maintenance, by the way, but also when it comes time to deployment, the monolithic nature of this application really gets in our way. So we change the search component, and then suddenly we've got to deploy all of the other components, even if they weren't ready to be deployed, and even if other developers were working on other features inside those applications that are maybe not quite ready for prime time. And of course, we solve that problem with pull requests and by making sure that we delay merging pull requests, but that creates other sorts of problems such as conflicts and this and that, cherry picking that leads to 2-week freezes, feature freezes on a stable branch while everyone does work in the dev branch. It leads to lots of overhead. There are ways you work around the pain of deploying this thing together as a single unit, but it is quite painful. And then another reality of the monolithic architecture is that different parts of our application, they don't all need the same thing. Search may need Elasticsearch, and our transactional email may need Amazon Simple Email Service. In some parts of our application, like fraud, they may be extremely CPU or GPU intensive. Other parts of our application might require gobs of memory. And by bundling all of these things together, which all have different requirements, they all need different things, and they all need different number of nodes to run on. By bundling them all together into a single unit and deploying that uniformly, we're creating a situation in which the entire monolith needs everything, and it needs the maximum amount of RAM needed by any part of the application, as well as the maximum amount of CPU and the maximum number of nodes required by the application as a whole. And of course, that leads to massive inefficiencies. Another, I think, less appreciated drawback to the monolithic architecture is that it violates something programmers value, which is encapsulation. And the easiest way to think about this is that, let's say we have a business rule. Our business says that anytime a user goes in and changes their user profile, they update their name or their address or whatever it is, then we want the user to receive an email notifying them of that change. Well, that's not so easy to do in a monolith, and the reason why it's not so easy to do in a monolith is because all parts of our application have direct access to the database that stores all user records, and no one can really stop you from going in and running a SQL update query to go ahead and change that information and do so in a way that does not result in that user getting the email that the business specified. As a result, enforcing business logic in a uniform way across a gigantic monolith application becomes extremely difficult. And you have to rely on convention and discipline and skill and training and other sorts of methods that work, but they're not very reliable, they're not very scalable. And then another serious drawback for the monolithic architecture is failure scenarios. So there's two types of failure scenarios. One occurs when we've got a bug in some component. And these types of bugs, they can be pretty serious. And when they affect one part of it, they really affect the whole. An example is, let's say search has a memory leak. Well, then every component of our application has a memory leak because it's bundled together in a single monolith. So, and not just search, by the way, but any component here that has any sort of a problem would be fatal to the entire unit, the entire monolith. So it's not very resilient. It doesn't give us a way to deal with errors in a resilient way. In summary, monoliths, really, they are anti-lean. And I mean that in the sense of lean manufacturing, lean software development, due to the fact that they couple together all these different pieces of the application into the same unit for packaging and deployment and operations and all of that. They dramatically increase the amount of sort of work in progress, the amount of stuff, value developers have created that's just sitting around in pull requests and not being used by the end user of the software application. They also lead to increase in process variation. So in any sort of monolithic architecture, there will exist points that are catastrophic, and they result in significant downtime and other types of situations, or you might not be able to ship a new feature for 4 weeks because something happened. And all that comes from the process variation that stems from the architectural coupling. And if you want to know the impact that these things have on the business, well, it's straight up from lean software development. Whenever you have increase in work in progress, as well as an increase in process variation, then it leads to an inability to responsibly deliver value. So quickly, on a timely and reliable schedule, deliver value to the users of the application. And as well as, okay, there's a side effect that's not so obvious. You can't ship stuff quickly, but also you can't learn quickly. And if you can't learn quickly and someone else can, well, they're going to learn a whole lot faster than you. and they're going to out execute. And so technology, your lack of sort of best practice technology implementation for your architecture can actually lead to you losing in a head-to-head competition. And that's why the tech companies, by the way, like Amazon and Netflix and so on, that's why they're all extremely dangerous. They are dangerous because they can put other kinds of companies out of business. They are so good. They are so agile. They're so lean. They can put other people who don't know what they're doing out of business. And that's why it's important to, at least in competitive industries, to take these things very seriously. Microservices, they came along and introduced a new type of architecture to solve all of these problems. And a microservice architecture, instead of having one that gigantic monolith that packages and bundles everything together, it divides the application into lots of different pieces. Each piece is called a microservice. And each piece is packaged, it's developed, it's maintained, it's packaged, it's deployed, it's upgraded, it's versioned independently of all the other microservices out there. You can really think of microservices adding lubrication. You know, it breaks, it fractures up that big monolith into pieces and adds lots of oil into all the pieces and allows them to flow together in a fluid fashion. And through this architecture, you can solve all of the problems of the monolithic architecture, all of them, 100% of them. So first off, maintenance becomes way easier. You change subscriptions, you add something to subscriptions that's needed by purchases, and you only need to update purchases. You know, that's it. Or actually, you don't even need to update it. You could just issue a new version of subscriptions, and then later you can go in, or the purchases team can go in and use the new functionality as necessary. None of the other stuff needs to be updated. So it radically simplifies maintenance. In addition, it simplifies deployment. When we update shipping, we just have to redeploy shipping. We don't have to touch any of the other stuff. So way less risky. We can do that very quickly, very easily, without a lot of risk. It simplifies. It makes more precise and more efficient infrastructure, because every different one of these microservices can have different dependencies, and they can require different amounts of CPU, different RAM, different numbers of node, different pieces of infrastructure. Some require Postgres, some require Elasticsearch. We're free to make every microservice only require and have access to the things that it needs to do its job, which results in efficiency and, of course, encapsulation. And then finally, even though microservice architecture, it doesn't mandate encapsulation, it's much easier to enforce encapsulation with a microservice architecture. So for example, we can make sure that no one can touch user account details, the database that the user account details are stored in, unless they go through the user account service. We can mandate that. That can be actually enforced at the level of infrastructure. So if any of these other microservices wants to change the user details, they have to go through user accounts microservice. And as a result, we can put any sort of business logic in there, such as sending that email notifying the user that their account details have changed in some way. Microservices, what they do really is they're pro-lean. They decouple our architecture. They just fracture that big old monolith into all these different independent pieces. And as a result, they radically decrease work in progress, and they result in minimization of process variation. And as a practical matter, what that means for your business is you can responsively deliver value to users, and you can learn from feedback. And the big companies that have these microservices architecture and have done them well, they can ship new features in an hour. And if you have a big monolith, you know that's not possible. That's not even remotely possible. You're going to have code freeze and all the other sorts of things that happen when you have gobs of people all working in the same gigantic monolith at the same time, implementing all their features. You're going to be shipping stuff more likely than not on a schedule of every few weeks, you know, on a good day. Whereas microservice architecture, a developer who is hired into one of these organizations can ship a feature his or her first day on the job in a couple hours. That's amazing. Now, that's the hope of microservices. And I would say microservices actually do deliver on that promise, but not without a few caveats. I love this slide. This is made by Daniel Wood. He gave a talk on microservices, and it represents, I think, the experience that some people have had when they try to build their first microservice application. Just ends up with everything being a gigantic mess. It's super complicated, and as a result, some developers are pushing back against microservice-based architectures because of the overhead, the complexity, the feeling that couldn't things be simpler? Why do we need all these microservices? Why can't we just go with the simpler monolith? And honestly, I'm sympathetic to that. But at the same time, we need to acknowledge that the pains solved by the microservice architecture, they are very real. And also the problems or the complexity, the challenges of implementing the microservice architecture are real as well. So there are good things as well as potential drawbacks. Let's take a look at some of the drawbacks. One of the challenges in microservice-based architectures is discovery. Discovery happens when subscription service, for example, requires the transactional email service. How does it know where to find that transactional email service? Well, that process is called discovery. And that's one of the challenges that we need to solve. In addition, we have the challenge of security. So back when our application was deployed as a monolith, basically the entire application is running inside a trusted environment. All parts of the code trust all other parts of the code. Your function A that's calling a function B can trust it. Whereas in a microservice-based architecture, the transactional email service is somewhere else. How do we know that's the real transactional email service and not a fake? How do we know for sure? We've got to do security. And by security, I don't just mean SSL. We can't just encrypt things. We've got to actually make sure that transactional email service is the one that we wrote and not someone else's one. In order to do that, there's lots of different authentication mechanisms that you can use, but you have to think about that. And there has to be some brain space and some code space and ops space devoted to solving that particular problem. In addition, we need monitoring, and we need monitoring more than ever for a microservice-based architecture, because microservice-based architectures have more moving pieces, way more moving pieces. Thousands of microservices, tens of thousands of microservices at a large company. And as a result, we need detailed metrics on how these things are functioning. So we have the ability to, when ops is deploying them and monitoring and managing them, they can see what's going on and they can identify problems and respond to those problems. And that requires super detailed metrics, and not only metrics, but logging, and not just logging, but a more advanced type of logging known as distributed tracing. Because basically in the monolith, our application functions as a whole, whereas in the microservice, it's fractured. And so to satisfy a single request for a little bit of functionality, a request comes in from the outside world, from the user or something, it's going to end up pinging through dozens or hundreds of different microservices. And we've got to keep track of all that information in order to do a good job helping us diagnose problems after the fact. And that whole distributed tracing, that adds a certain amount of complexity. We also got to think about recovery. So what happens in a failure scenario? Catalog goes down. How do we restore that service? And not just how do we restore that, but what if catalog is depending on the user account service? We've got to think about user account service goes down. What happens to catalog? We've got to think about failure recovery. We've got to think about being resilient in the face of transient errors when the downstream dependencies that we have are malfunctioning for short periods of time. Routing is another concern. So when we get a request and that request is designed to go to the fraud service, there will be, in general, lots of different nodes running the fraud service. How do we decide which request gets which node? It gets executed by which node? And that's the routing problem. And the routing problem, routers can be used to do lots of different things, but one of the things they can be used to do is versioning. So we can have fraud 1.0 running concurrently with fraud 1.1. And that's very common in advanced microservice architectures. We also have to think carefully about deployment. And that's because in the monolith, we have our giant monolith that we ship out. We package it in a container and we deploy it. And we scale that, and that's all very straightforward. But deployment is much more complicated in a microservice-based architecture, because any given microservice is deployed on a variable number of nodes. They're all sort of independent. They're not necessarily connected. Some microservices might only be deployed on 2 nodes. Others might be deployed on 10,000 nodes. It depends on the needs of those. And also we have versioning to think about. So we may have concurrently, we may have subscriptions 1.0 living alongside subscriptions 1.1. That's something that could happen. Load balancing is another consideration. So if a request comes into fraud, we've got to make sure we don't overload any given node with the fraud service. We've got to make sure we balance that across different fraud nodes and make sure that the overall traffic remains fairly constant if you look at that on a per node basis. And then finally, we've got to worry at least a little bit about traffic control. So sometimes we don't actually want to impose certain limits or other types of policies on certain services to avoid problems like a new user account registration service. We may want to do some traffic control or enforce other policies associated with that. And that's additional work and complexity that we have to worry about with a microservice-based architecture. That's a lot of different stuff. It is a lot of different concerns that you have to worry about when you're trying to do a best practice microservice-based architecture. And the reality is that, yeah, some people have had bad experience with microservices. I can totally see if you throw a new microservice project at a team that's never done it before, honestly, there's just a lot of learning involved, and it can take a lot of experimentation with different technologies and tools and trying to understand exactly everything that goes into creating one of these killer microservice architectures that have been attracting companies to that style of developing applications. If you want the same benefits as a big company who is successfully using one of these next-gen microservice-based architectures, you need to pay attention to detail and you need technical expertise. A lot of things can go wrong. And if you do have that technical expertise, if you do pay attention to the details, then you can reap the same benefits as the big companies that have been successfully using these architectures. I don't even think there is a big tech company that does not use microservice-based architectures, which just shows you how successful it's been. And I think you heard earlier in the day from Fugo that it can even make sense for startups, basically. There's no reason that you have to be in Amazon before you turn to a microservice architecture, because the tooling out there is becoming so good that the cost of deploying best practice microservice architectures has gone down. All right, so in the face of these challenges, where are things going in the future? And I'm going to rush through this final section. Okay, I have 10 minutes. Fantastic. Okay. So I'm not too far behind. Kubernetes is a fairly new technology that has become almost an operating system for deploying and running today's cloud-native applications. And even though Kubernetes is not designed specifically for microservices, it is nonetheless an extraordinarily good fit for deploying microservice-based applications. And it provides a lot of the infrastructure required to deploy and operate, manage, and monitor microservice-based applications. And the fact that it's become so successful and so synonymous with cloud-native applications is a real boom, because it means that there's a whole developing ecosystem that is tailored to adding. Kubernetes does not have everything you need if you want to deploy microservice-based architecture, but it has a lot. And the fact that it's become the sort of de facto standard for deploying cloud-native applications has encouraged a lot of open source projects and frameworks and vendors to produce Kubernetes compatible tooling. And it's also led to evolution of the Kubernetes platform, because now it has features in there that is designed basically hook points for you to add other types of functionality that microservice architecture needs. And so I would say that Kubernetes is definitely a key part of any current or future microservice-based architecture. You need to be running Kubernetes. You need people with Kubernetes expertise. You need training around that and so forth. Kubernetes has architecture similar to the one shown here. It basically controls all these different kubelets. They're called. It has a proxy for each one. It has a scheduler. It has all the different pieces to monitor and deploy this. It can grow and scale. It can do restarts. It can assist with security concerns to make sure that things are relatively secure. It even has a bit of functionality in there to help with discovery, depending on how you choose to solve that problem. So you can solve lots of parts of the microservice problem by using Kubernetes. Kubernetes does not solve everything, however. It doesn't have deep insight into what a microservice is. Kubernetes is much more general than that. And so to assist with some of the other concerns that I mentioned, a lot of people have turned to so-called service meshes. And the top 3 service meshes out there that assist with building and deploying a microservice-based architecture on Kubernetes are Consul, Linkerd, and Istio. And these 3 solutions, they all have an architecture similar to the one you see here, where when you deploy a microservice, you actually deploy it together with a sidecar proxy. It's called a sidecar. What it is a proxy. And these sidecars, what they do is they act as a little envelope that totally encloses the microservice. And all communication into or out of the microservice, it goes through the proxy. And as a result, the sidecar, it has full insight into everything that the microservice is doing. And that helps solve a whole host of problems. For example, that solves monitoring and distributed tracing and other types of concerns because they know the traffic in and out. So they can actually provide for free a lot of the features that you would otherwise need to bake into your microservice. They can assist with recovery. They can perform routing. You in a service mesh, you have not only all of the different sidecars that are attached to all your microservices, but then you have orchestrators and monitors and supervisors that sit at a higher level and keep an eye on stuff and make sure it's doing what it's supposed to be doing and handle concerns like load balancing and traffic control and enforcing of different policies and helping microservices discover each other and doing security and so forth. The quality of these technologies is becoming very high. It's becoming easier and easier to get all of these features that I mentioned earlier in a cost-effective manner by using one of these Kubernetes-friendly service meshes. Another very interesting area that I think is going to affect the whole microservice framework is this idea that even though service meshes are extraordinarily useful, you can see Kubernetes, it keeps on expanding the types of functionality it's offering. It's almost eating into service mesh territory, really. Like Kubernetes keeps on absorbing some of these features at the fringe of the service meshes. And then in addition, frameworks like Spring Boot, for example, keep on, have that long history, but also they keep on adding features to make it easier to ship best practice microservices. So I honestly think that there's a chance, a non-zero chance, that at some point the service meshes might fade away into the background and become more niche. I think at some point we might only be using smart next-gen microservice frameworks that bundle all of these rich features together and that deploy natively into Kubernetes and take advantage of all the features that it continues to add to make it more friendly for microservice deployment. So I think that's a really interesting possibility to pay attention to. And then in addition, we have a whole host of next-generation so-called stateful functions or stateful serverless or stateful workflow solutions that are designed to shift the way you think about building distributed applications. And these technologies are none of them are strictly focused on microservices per se, but the fact is this class of technologies, what it's trying to do is enable ordinary developers to write business logic and not have to pay attention to infrastructure, not have to pay attention to databases, okay? Don't even consider that databases exist. Don't consider that there are such a thing as microservices, version microservice. Forget as many details about infrastructure as you possibly can and focus only on business logic. And they're trying to do that in a variety of different ways, but ultimately all of them are trying to create this concept of a computer, basically, that basically program as if you were working on a computer that never goes down and that just runs forever, and in which all the data that you touch is persistent. So you update a variable and that just is persistent. It can survive forever. That's a new way of thinking about computing. And it is highly likely, in my opinion, that this class of solution ends up altering the way we build and deploy microservice-based architectures. It could radically simplify it. It can simplify it because when you offer a programmer a constrained environment in which they don't have to worry about infrastructure, then you can provide a lot of the stuff that I mentioned before, like security and provisioning and deployment and monitoring. All that stuff you can provide for free because your constraints liberate and liberties constrain. as the saying goes, you give the user a small bit of functionality, and then you can provide a very solid foundation that enables them to forget about the infrastructure, and you handle that with the platform itself. So this is a space to keep an eye on. I do think that it will end up changing the way a lot of companies, especially the non-tech giants, end up shipping microservice-based architectures. And then finally, I should mention that all of these challenges, they do have solutions, and they have open source solutions in many cases. And actually, for every one of these different challenge areas for microservice-based architectures, there probably exists 2 to 20 different open source solutions you can use to solve them. And there's no substitute for training. So equipping your developers with training, whether that's books or workshops or whatever, also senior expertise, making sure that your teams have someone on them, ideally a few people, who have built and deployed successfully a best practice microservice architecture can go a long way to ensuring project success. And then finally, there's plenty of consultancies out there. My friends at Scalac, for example, and my own company, Zyverge, who you can pull in to help oversee a project or provide some extra help in order to ensure a successful execution of a microservice-based architecture. So, in summary, although the microservice-based architectures are complex to do right, new technologies like Kubernetes and service meshes, maybe even smart microservice frameworks, are helping to democratize microservice technology. And all that said, there's no substitute, at least at the current moment in time, for expertise. So training your people and making sure you have people who've done it before on the team working with you is the key to having a really good outcome for one of these next-gen microservice-based architectures. And with that, if we have any time, actually, I think I used up all my time, but I'm happy to say this was not 2 hours.
Thank you very much, John. That was a great presentation. And we have a couple of questions and have 4 minutes to the next speaker, but I will try to pick maybe 1 or 2. So the first question. Hi, John. Could you explain how Zio Web, which I think is Zio Microservices now, will help us to solve the problems of microservices-based architecture?
Yeah, that's a great question. And I think my vision for Zio Microservice is to basically become that smart microservice framework that you use to deploy microservices into Kubernetes-based architecture. That it would bundle together a solution to all of the different concerns that you have when you're building and deploying microservice-based architectures, taking advantage of all the features in Kubernetes. Basically, I would envision Zio Microservice to be an alternative to a traditional microservice-based library or HTTP library or gRPC library and a service mesh. So if you take basically the best parts of a service mesh and the best parts of an ordinary gRPC or HTTP library, bundle them together into something that's type safe, composable, very user-friendly, enables you to be very productive, fits well into the Zio ecosystem, and runs natively in Kubernetes, that would be my vision for Zio Microservices.
Okay, thank you. And maybe another one, like a comment or the question, I feel like we end up creating microservices that only ever do one thing, and it feels like too much overhead. How can one determine the correct level of responsibilities when drawing boundaries?
That's a great question. I think there's two answers. The first one is the overhead for creating and deploying microservices is too high. It's way too high. You should be able to create and deploy a new microservice in 30 minutes. Honestly, I believe that should be possible. It's not possible right now, but hopefully as we invest more into this space, it will become possible. And then the other thing is the correct level. I think you need to look at basically when you're packaging up everything that goes into a microservice, you need to look at functionality that's related as well as that has similar dependencies. So if you have a bunch of functionality that all needs to talk to Postgres and use the user accounts table, as well as these other 3 different functionality, that's a sign all of those need to be packaged together. I think it's always a hard question. I don't think that there is a scientific answer, but I think looking at the dependencies, looking at how related they are in terms of functionality, and looking at how often is it that changing one would lead to possibly changing other parts inside the same module can all help you draw that division between microservices such that you don't have to pay too much. You shouldn't be deploying it's too costly to deploy individual routines as microservices.
Okay, so we have space for one more question. I think that even paying attention to detail, something can go wrong. There are architectural smells that could indicate that my microservices are starting to break down. Could you refer to that, John?
Okay, architectural anti-patterns for microservice-based architectures. Well, I would say if you're following all the best practices, you're in a reasonably good place. But like you point out, that doesn't guarantee that everything's going to go well. So, for example, one of the concerns you have to look at is, do you have continuous deployment set up? Are you able to literally deploy a new are you doing canary-based deployment? Okay, so do you have some protection? When you roll out a new service, do you have a way to evaluate whether or not that's functioning properly? And if you don't, there's something wrong with your architecture. You don't have the mechanism, the machinery necessary to figure out if things are going wrong. Also, can you do instantaneous rollbacks? If 1.1 is leading to problems in production, can you instantaneously, in your canary-based deployment system, can you roll back to 1.1? Yeah, or 1.0. If you can't, there's a problem. I think the other question about how fine-grained or coarse-grained your microservices are is a good one. So even if you follow all best practices, you could have really an architectural anti-pattern by deploying lots of too fine-grained microservices. You know, if you're shipping individual functions as microservices, you're setting yourself up for way more overhead and cost than you ideally would be setting up yourself up for, and you can do that while still following all of the best. So having the right level of the right number of individual routines inside of a microservice that all relate to some core area of functionality is critical. I think some of the work that people have done, like Bob Martin and so forth, the Agile folks, basically, in elucidating the principles of good object-oriented design, there's a lot of useful there's a lot of literature that you can pull into the design of a successful microservice architecture on what's the right level of functionality that every one of these units should ship with.
Okay, yeah, there are a lot of questions from our audience, so maybe just the last one. What is the best approach to implement microservices, Kafka or Akka with ZIO technology?
Yeah, that's a good question. So obviously I would use ZIO no matter what. As for Kafka versus Akka, I think Kafka has opened up the door to implementing microservices in a different way, stateful microservices in a different way, because you can use the Kafka log basically combined with event sourcing or some other similar pattern like that to really do a lot of the things that formerly you would have had to use Akka cluster in order to do. But I think that ultimately the key there is going to come down to latency. If you have super low latency requirements, then that's going to probably shift you more into the world of using Akka. So building something on top of Akka cluster, and there's a ZIO library that can help you do that. If you have maybe higher latency requirements, or maybe you're more in the realm of like data processing, ETL, something like that, that's probably going to push you more into the Kafka. Ultimately, I think it's going to come down on the details of your business requirements, which of those two different technologies you choose.
Okay, thank you very much once more, John, for joining us. It was always a pleasure to have you.
Thank you for having me.
Thank you very much. And yes, we are moving to another speaker. Another speaker is Nathan Selinsky from Wix, backend engineer. And unfortunately, Nathan wasn't able to join us online just right now, but we recorded his talk earlier this week. So Nathan will be talking about event-driven patterns for your microservices architecture. And we just replay right now this recorded talk. Enjoy. And you can always ask questions in the chat. The questions can be answered by Nathan just after the talk, but we will transfer all the questions to Nathan and get back to you with the answers. So please just drop us a message at info@scalac.io or using Twitter. We are happy to answer any questions. It's really a great presentation. So Nathan Selinsky from Wix will be presenting right now.
My name is Nathan Selnitsky, and I'm a backend infrastructure developer at Wix.com. And this talk is about the key patterns that I have implemented or have witnessed implementations of at Wix that have enabled us to create a robust, event-driven, distributed microservices environment that can easily handle increasing scale and traffic and storage needs. But first, a few words about Wix. Wix is a website building platform that allows you to manage your online presence and manage your business online. And we have more than 200 million registered users from 190 countries. About 5% of all internet websites run on Wix. Our microservices environment comprises 2,000 individual services, and we have more than 1.5 billion Kafka messages produced per day, which means we have quite a lot of event-driven use cases for our microservices. And the agenda today is going to be about how we can move away from monolithic design and towards microservices environment in the event-driven style. So we have a consumer project that's about a pattern about how we can create services with the materialized views that help us with optimizing queries and also moving away from the monolith to disjoint microservices. And then the second pattern is event-driven from end to end. So here we see how we can combine Apache Kafka and WebSockets in order to have full event-driven flow from the browser all the way for all the cooperating microservices. Then we'll touch on the zero latency key value store pattern, where we can have storage that we can access in memory with zero latency on top of Kafka and Kafka events. And then we'll see how we can actually perform event processing in our microservices, but with the guarantee of exactly once processing. So we can make sure that for high-risk operations, there is no data corruption. So we started off in the industry with our monolith that did everything. And then we saw there are quite a lot of advantages to actually moving from monolith to a distributed microservices system. That means that services can be deployed separately, can scale up separately, and have different requirements and needs. But what about the database? So if we have still in the monolithic approach, one big database to support everything, that means that we have mutable state that is shared by all of these services, which is not good, and high contention for possible that all of these services may need to access the same parts and increase latency and reduce performance. And also no flexibility of choice. We'll only probably use one relational kind of database, and that's it. And that's really not optimized for all kinds of needs for our microservices. So instead of that, usually with a microservice, you'll have the data encapsulated behind the service. Each microservice will have its own kind of database, offers optimal flexibility. Maybe you want NoSQL, graph database, whatever suits your domain logic. And also schema can evolve easily without needing to worry about mutable shared state and other conflicts with other services. Now let's talk about microservices communication. So if you take, for example, an e-commerce services, we can see here we have the checkout service, and it requires all kinds of collaboration from other services here, like payment service, user service, and inventory service. Now, we can go with the classic request reply model and have HTTP or RPC requests be done from checkout service to these services, but that's a bit problematic. First of all, we encapsulated the database, meaning that for each of these requests, the service will need to go to the database, fetch the information, and bring back the result. So we're doing these requests one by one. We don't do any joins here between these tables because each is in its own separate service. So this is quite a slow operation. And also, there could be network issues or something that it makes the service go down or maybe a bit unreliable, meaning that now the checker service that needed to have this information online now because of some request from the browser, it doesn't have it. So it will need to fail the request back. So it's really unreliable model. Now, if we introduce a message broker between our microservices, then we can have a bigger degree of reliability. Messages are produced to a cluster of brokers, so there are a lot of cooperating brokers with a lot of redundancy between them. All of the data is replicated between the brokers, so we have a much higher degree of reliability for these message broker clusters. And also, because we're producing messages and consuming messages, we're actually completely changed the flow model. So flow control is moved from the sender here, which doesn't really know what's going on other than it produced the order created event, to the receiver. So the control here is going to the consumer side. And this means a much more robust approach, because even if the producer is currently down, we still have all the events that it produced up until now to consume. And this solution means that the consumer can consume it in its own pace and really gain the full advantage of not needing to have an online server to call. Specifically, this talk focuses on a message broker of type Apache Kafka, which you can define as a distributed log broker, where each topic that messages are produced to is divided into partitions. And these partitions have linear scaling, meaning that if you need to have bigger traffic, bigger throughput, all you have to do is add more partitions, and then you can handle more traffic. Of course, you also need to have more instances for your microservices to have this increased processing rate. And these partitions are basically commit log files where events or messages are written at the end of the file, which means it's much more faster than other kinds of data storage models. And you can see here that message producer produces the message at the end of the partition, and data can remain here actually indefinitely. It's not like with traditional message queues, where once the consumer consumes the message, it is actually removed from the topic. The messages stay basically forever. You can set it up, although the default is to serve it for 1 week. And then consumers are just passed through sequentially each partition, and once they finish processing a message, they will commit it, meaning that if there's some restart or the service starts up again for some reason, it will start off on the assigned partition from the first message that is not committed yet. So this way we have the efficiency and throughput of processing from an append-only file in a very fast manner. It can also be a lot of times in memory, and still have the flexibility of knowing which index to start consuming from. And this data model is immutable because we only append, we don't change data in place, meaning it's much more resilient and much easier to debug as well. And we can also guarantee that processing will eventually succeed, because if there is some failure with processing the message, we know that because of the sequential property, we can eventually retry and retry until we succeed processing the current message and only then commit it. So if we look at our ecom example and try to switch it to the event-driven model from the earlier request-reply model I showed you, then here we'll have communication between a checkout service and the other services actually done via the intermediary, the Kafka broker. And each topic will have each service will be in charge of its own topic. So the payment services has the order topic that it can fetch orders from and actually perform payment. And the user service is in charge of the user's topic, etc., etc. So we can think about these topics as actual storage of that the checkout service can easily access and consume messages from, or in the case of orders topic, produce messages to. And that means that we have much greater decoupling, much more flexibility. You can also cache some of the information in your own service, and you are completely decoupled from the need to just query each service separately and have much better performance. Okay, great. So like I said, we're going to talk about the 4 specific patterns. Now we're actually going to drill down on what it means to do event-driven style of programming for microservices. And these are based actually on a blog post I wrote, and very popular. It helps a lot of developers and architects. And all these patterns are used quite widely at Wix microservices. So the first pattern is consume and project. So imagine that you have a service that it has very high throughput. In our case, we have the metasite service that stores all of the metadata that is part of a Wix site, including which applications are installed on the site, what's the site version, who's the site owner, all kinds of relevant information. And we have all kinds of other microservices at Wix, including verticals like stores or booking, scheduling, and restaurants that actually require to get information of this monolithic service, the metasite service. And it had a traditional database with a large metasite object serialized for the database schema, and a lot of read and write requests. Actually, it got up to 1 million requests per minute. So quite a heavy load and contention on the database. So the metasite team they thought about how to reduce this contention and get better reliability and performance and not risk database failure. And they did this by first taking a part of the data, only the site installed applications, and seeing how they can actually remove these requests from a site service. How did they do that? So first, they actually produced to Kafka each and every change that is done to the database. So a site is updated, its metadata is updated, and they produce the metasite object to the Kafka broker with all the changes. Then they created a completely new service called a reverse lookup writer that it consumes these messages, events on updates to metasites, but it only filtered to get updates on which apps are installed on the site. So it acted as a filter or a projection and only consumed the site application installed context and put it in a brand new database table. And the third part here is that they had another service called a reverse lookup reader that actually was in charge of reading from the database. And now we had queries that are optimized just to get information on apps installed, and it can easily be fetched from the database. So what are the advantages of this kind of migration and new architecture? So first, we produce messages instead of serving them. So that means massive load reduction on the original database table with the entire metasite object. Second, because we projected the information, then we can have highly optimized queries like materialized views to only the information that is highly needed, like which apps are installed on the site for our different various verticals. And also importantly here, there is this read-write split between a writer service and a reader service. So with this approach, it means that it was really easy to only scale the reader databases. So we can have replicated instances of the data for read-only state. And this means that we can have a lot of replicas in only one original master database to get writes into, which means it's much more resilient. We know that these read-only databases cannot be corrupted and are easily scalable because you just need to add more as you gain more throughput and popularity for these kinds of requests. So it means that by adding more services and utilizing the power of Kafka, we could really switch the metasite service from its monolithic approach to a more distributed microservices approach and gain much better performance and reliability. Great, so the second pattern is event-driven from end to end. So we're talking about how we can have events be part of browser to service interaction, which may sound a bit weird. For instance, let's look at the following use case. We have a long-running asynchronous business process. So imagine that you want to have a service that imports contacts from various platforms like Gmail and stuff like that over into the Wix configuration system, CRM system that manages the Wix site owners, contacts, and visitors. And maybe they want to send some email to notify something. They want to keep all the contacts that they have and put it on the Wix platform. Cool. So we want to start thinking about how to actually create this architecture. So we have a contacts job service, and all its job is to actually create these import jobs. So it produces a job, maybe separate jobs for importing from Gmail or from Outlook or from other stuff, or maybe other concerns it has. Maybe they need to split up big lists of contacts into smaller jobs. And then we have the contacts importer service that will consume these requests and actually do the import actions themselves. Now, if you see, we're producing a request to Kafka, but we cannot actually get any request back yet because the operation here is asynchronous. We're actually sending an event. So how will the browser know when the import process is finished or it's 50% done? So for that, we're going to actually have the browser subscribe to get WebSocket notifications from Wix's WebSocket service. And then when it requests to import CSVs, for instance, from the front-end service, then it will also provide a channel ID, a WebSocket channel ID, where results can be brought back to the browser. And this channel ID will go to the import job request coming into Kafka, including the channel ID. And then when the consumer is finished with processing some job, it can actually update the WebSocket service that job 1 out of 10 is completed. And this notification can be brought back to the browser. And the browser has no idea that multiple services are part of the processing of import business logic. It's completely decoupled, but for the user, it's completely seamless. Now, another cool thing that you can do with Kafka is that you can actually take these job import requests and replicate them across different data centers and have the actual operation of import be done on a different data center. Maybe that's good because we know that the best Outlook server for getting good performance when doing imports from Outlook is in an Asian data center. So we get the original request on a European data center, but then all of the Outlook requests will only be processed in Asia. So it's a completely distributed global operation, event-driven from end to end, from the browser all the way to the last involved microservices and back. So you can see here that no polling is required. We don't need to keep some status in a database and have browser keep asking what's going on, is it finished yet, and keep updating database and making sure that we have locking or optimistic locking, stuff like that. We don't need to do any of that because we have complete event-driven flow, no polling, and we can just bring back notifications when jobs are done. And it's scalable because it's really easy to spin up more import job workers as required, like we talked about earlier. And the replication property of Kafka topics means that it's really easy to have cross-DC requests and cross-DC processing. Great. So the third pattern for this talk is the zero latency key value store. So this talks about how to have information that you want to have readily available and not keep up the user request waiting from the browser. So for that, we have another feature of Apache Kafka brokers that's called compact logs or compact topics, where we have, for each record, we have a key and a value, but the Kafka will not delete messages that are stored after 1 week, but instead it will remove messages where there is a stale value for the same key. So in this slide, we can see that for key 1, there is already an updated value of V2. So that means that key 1 and V1 can actually be removed. So at Wix, we created a data structure called key value store reader that has an in-memory map where on the service startup, we'll read sequentially all the partitions from the compacted topic and create an in-memory representation of this information. So we see that for key 1, V1 is changed the value to V2 as the processing is progressed. And then we add key 2, V1, and key 3, and so on. And once the startup phase finishes, we have a complete representation of the key value store in memory. So of course, it's not good for data that can basically, data sets that can basically infinitely big. It's more for data sets that you know will be contained in size. For instance, we have the business manager service that stores information on the countries, which countries currently Wix is operating in, for instance. So we have the countries topic in Kafka, and it can load that information. And we can also have, for instance, the booking service that is in charge of helping site visitors book lessons like yoga lessons, stuff like that, from Wix site owners. And here it's very important to know what's the current time zone for each country. So we have the time zones topic, and we have a reader for bookings to actually keep all of this time zone data in memory. So now let's look at how we update this memory. So for that, we have the key value store writer data structure, where the business manager is updated that a new country has now Wix operating in it, for instance, South Sudan. So we have a simple producer here, just produces a new key value for South Sudan to the country's topic. That's all, nothing special here. But then we can have the business manager service itself or other services have a key value store reader for country's topic themselves. And it has a built-in consumer in order to get updates online. So once business manager updated the country's topic, and it means that bookings can have immediate update also for its in-memory representation. And now bookings notes that it needs to add for its time zones storage the time zone for South Sudan. So it looks it up in some HTTP request and then brings it back, updates the time zones topic via the producer, and voila, we have the South Sudan key value for the time zones key value store. And then we want to update some data, some time zone for Albania, for instance. So we have key value store writer, update that, and it's updated automatically because we have the consumer listening for updates. And then other services can also have their own stores, etc. And what's nice here is that all the different services in the ecosystem are kept up to date all the time because they have this consumers. And so we not only have zero latency for the bulk of the key value store that is read at the beginning, it's also kept updated throughout the lifetime of the service. Okay, so what does this pattern give us? So we have zero latency key value storage for the dynamic configuration, like time zones, like available countries. Notice that compact topics is still a topic. Other services can consume it regularly and get updates, like we saw. Now, like I mentioned, it's very important that you won't use it for general purpose data sets that are dependent on, I don't know, scale of traffic and stuff like that, because then you will not fit into memory. For that, a better approach will be to have a disk-based database that you use and an in-memory cache on top of that, it could be compact topic, or maybe when scale grows, it could be regular topic that gets updates from the database, and you just decide how much of the topic to keep in memory in the beginning, so it's more scalable. Great. So the last pattern for this talk is having events done in transactions, meaning that no matter how many times Kafka may accidentally process the same message, we don't alter the state of the side effect of the events that causes the side effect. It keeps being idempotent. And let's see how it can be done quite automatically by using new features that Apache Kafka provides. So we have here a classic e-commerce flow where we have payment service, and we're doing this in event-driven fashion. It announces to the world that a payment was completed. It produces an event to Kafka. Then we have the checkout service that is consuming this from these payment topics, and it also produces an event that an order is completed along with all of the items that are part of this order. And then we have downstream services that consume these order completed events and perform side effects. Like delivery, they want to make sure that it's packaged and delivered all of the items on the order. Inventory needs to be reduced in order for correct operation, of course, and an invoice needs to be sent along with all of the items in it. Great. So, of course, we can have multiple situations here where, because of some restart or failure, we'll have multiple times where we consume messages, and basically we can end up in a situation where we handle the same event more than once. But that's not good, because then we may deliver the product more than once. The inventory may be incorrectly decremented twice or more, and stuff like that. So the traditional approach to solve this is to have a database that keeps track of which completed orders have been successfully processed, and these services will need to mark when they finish processing it, and have some maybe optimistic locking and stuff like that, or regular locking for your database queries. But that's quite a lot of boilerplate that could be avoided. So how we can avoid it? So we can switch each part of this flow into being more idempotent. So for instance, the producer at the beginning of this flow can be changed to be to change to an idempotent producer, and that means that it will make sure that the message is only produced once to Kafka. It does that by attaching an offset to the message. So here you can see how it will make sure that it won't produce the message more than once, because it says, okay, I produce message 0 and put it in offset 0. I produce message 1, put it in offset 1. And then the producer says, okay, there was some restart, it didn't get an acknowledgement, and it says, I'm producing message 1 again. But then Kafka will say, wait, I already have message 1, and it completely ignores it. Now, about the rest of the flow here, it's a little bit more complicated than the idempotent producer at the beginning. Actually, Kafka creates a transaction between the consumer producer here, or processor, and the downstream consumer. And this has quite a lot of details into it, which I won't get into because we are short in time. But I'll give you more information at the end of this talk, so you can query it yourself if you're interested in how exactly these transactions are actually implemented. I will say that the consumer side here will only view messages after they are successfully consumed and produced once by the service in the middle. So there is a bit more boilerplate to setting up these Kafka transactions, and you will need to perform tuning because the more messages you put in a transaction, the less the overhead of performing this transaction will matter, but you will incur latency because the downstream consumers at the end will need to wait for all the messages to be produced for this transaction, and only then, when the transaction is completed successfully, will they be able to consume it. So there's a trade-off here. And database updates or third-party calls are not covered. They are not part of what Kafka has control over in order to make sure they are idempotent. But you can deduplicate writes to database by using the Kafka record offset itself as a version to make sure that you don't update for the same version twice and decrement the inventory twice mistakenly. And I wouldn't recommend turning on these transactions by default. I would only use them in critical flows where exactly once processing is mandatory, like with payments processing, for instance, but not for any old event processing that you perform in any microservice because of this overhead and more complexity. And if you want to have more information, I actually gave a talk on the matter of exactly what's delivered with Kafka. And I put the link here in SlideShare. So don't worry, you'll have the link to this talk. And I want to summarize now. So Wix developers have employed these event-driven patterns to make the microservices more decoupled, resilient, and scalable. And you can also, a lot of the patterns here have partial implementation done by our Apache Kafka SDK client that we have for the JVM called Greyhound. So it's open source and you can check it out as well. It has a lot of cool features, enable parallel processing and consumption, resilient retries, and batch consumer, and a lot more. So you can check it out on this link. So thank you very much. Really enjoyed giving you this presentation. And here are more resources where you can find out about the patterns that I gave in this talk. I have 2 blog posts on this matter. And also there's a great blog series about moving to event-driven style development of your microservices by Ben Stopford from Confluent, the company behind Kafka. The disadvantages of having shared database by Chris Richardson, also a great resource, and the talk I gave on exactly once delivery as well that you can check out. And all the links here I put in SlideShare, so you can just find me on SlideShare and find the slides there. You can also follow me on Medium and Twitter for everything that we are up to in data streams team at Wix around event-driven architecture, Apache Kafka, and also software engineering best practices in general. And you can also check out my website at natansil.com. And there you'll find links to all the previous talks I gave at conferences and more material. So thanks again.
We would like to say a big thank you to Nathan. I hope that now you better understand how Wix is dealing with microservices. And because we have slight delay, so we are just starting our new talk, our new session. Let me welcome our next speaker. I would like to introduce Hugh McKee, developer advocate for Lightbend. Scalac and Lightbend are partners and trying to do our best for our clients. So Hugh will be talking about the design, microservices design patterns. Welcome, Hugh.
Thank you.
Take it away, Hugh. Thank you.
All right, thanks. Let me share away here. All right. Hello again, everyone. And like we were saying, this is a talk on microservice design patterns. And I'll try and go a little bit quick because I know we're running a little bit behind on the schedule. But before I get into this talk, I wanted to just take a little bit of time to flex your mind. Maybe some of you have been sitting on, for many of the talks that came before this, and lots of great information. Maybe some of the things I'm going to talk about you've seen before, but maybe not. And some of the things I'm going to cover might initially seem odd, counterintuitive, mind bending, those types of things. We'll see. But so I want to kind of flex your brain a little bit and start out with a couple of fun things I ran into recently. This was something on Reddit. This guy was handling these riddles very, very quickly. So I want to show you two. And it's just kind of just to demonstrate flexibility in thinking. You know, I'm calling it pattern flexibility. So this first riddle is, there's a boat full of people. The boat capsizes and not a single person gets wet. So how can this happen? So if we had more time, I'd kind of wait a little bit and let you think about it and like, okay, how could this happen? Not a single person gets wet, but you say you have this boat that I have in this picture here that I just grabbed, and say the boat capsizes and everybody goes into the water. Nobody gets hurt, but they're in the water. But how can they not get wet? Well, the answer is that they're all married. So yeah, when I first saw this, it's like, wow, okay, that's a good answer, but I would never, I don't know if I would have come up with it. And I was annoyed because I didn't come up with it. This next one even annoyed me even more. I didn't get it when I first saw it. And I like these kinds of problems. So this one is, you have this mathematical expression, and the expression is 5 plus 5 plus 5 equals 550, which is obviously wrong. So the challenge is add one line to this expression to make it correct. So I looked at this one and it's like, okay, how can I do this? And I was thinking about all kinds of different things. And anyways, the answer was add a line on that first plus sign. I hope you can see it there with the first plus sign. So it changes the 5 plus 5 to 545 plus 5 equals 550. And I go, darn, why didn't I get that? Why wasn't I flexible enough to think about that? And so in this talk, I'm kind of asking you to be open-minded. So
Hugh, one thing, we don't see your presentation.
Oh, sorry.
Yes. Could you?
I'm sharing.
Could you please double check if you are sharing through this?
Can you see it? No?
No, unfortunately not.
Okay, let me try something else here. I'm just using, how about now?
Still not.
Let me go back to StreamYard.
Yeah, because you have to do this from StreamYard.
Entire screen share. Oh, darn. I got it. I think I got it. You see it now?
Yes, now
All
it's
right.
Perfect. Yeah.
Should I start again? Let me go back. I want to show you these things. Sorry. So flexible mind. So the first one, I think you heard me, boat full of people, capsizes, not a single person gets wet because they're all married. The second one is this mathematical expression, and the answer is add a line to the plus sign, which gives you 545 plus 5 equals 550. So again, this is just kind of trying to keep things flexible in our brains, trying to be open-minded to looking at different ways of doing things. So the agenda that I have here kind of goes in this flow, and it's kind of an evolutionary flow of going, I'm using a transportation analogy here, like going from horse-drawn transportation to vehicles on the road to, flying in the air, transportation via air. And then now we're going more and more into, say, into space. This is kind of the evolution I'm kind of walking you through here with the ways, you can implement your microservice systems. And it starts with the monolith. The thing I want to point out here is often when we talk about the monolith or when we talk about microservices, there's a lot of attention on the code, but also want to draw attention to the data. That in a monolith, it's common that there's a monolithic hunk of code that makes up the application, but there's also a monolithic database that makes up the application. And a pattern that is often used when folks first make their first, say, entry into building some kind of a microservice system and adopting these types of technologies and architectures and patterns and so on, is that the code is broken up, but the data isn't broken up. Because sometimes it's a lot easier to get approval to break up the code, but it often is much more difficult, especially if you have legacy stuff that you're trying to evolve to break up a database. Not saying this is a bad pattern, this is a good pattern. This is a great, first step type of thing. And I'm also showing the microservices here kind of a little bit kind of tightly grouped together. They're each one of these little boxes represents the different microservices, but they're kind of tightly coupled. And I'll explain what I mean by tightly coupled in a minute. And then kind of moving along, I'm trying to represent here visually that the design has evolved to a point where the microservices themselves are more loosely coupled, but it's still, the database is still monolithic. And I'm using this term microlith, and I'll show you what I mean by a microlith in just a second. And then the final part I wanted to cover here is that it's not only the code that has been micro-sized, but it's the data that's been micro-sized as well. And some of the pros and cons of that. So that's what I'll be covering also. So what's a microlith? And the term is something that I've seen in different talks. Our CEO, Jonas Panera, the creator of Akka, uses this in some of his talks. And it's the term for microlith is distributed monolith. And generally, there's kind of two big characteristics. The microservices are tightly coupled, and the data is monolithic. So by tightly coupled, what I mean is that tightly coupled microservices have this characteristic where the microservices talk to each other restfully, making essentially remote procedure calls. And it's synchronous, that there's a request made from one microservice to another. The requester is waiting for a response. So, there's that kind of synchronous, restful interaction between the services. So here's an example. Got a client on the left. The client makes a request to microservice A. Microservice A makes a request to microservice B. So what's happening here is microservice A, when it gets a request to perform an operation, it needs to ask microservice B to perform part of that operation for it. So A makes a synchronous request to B. B gets the request, but also with B, it needs to ask C for it to do some work for it. So B gets a request, it starts processing it, but then it makes a call out to C. Then C's got the request and it's working on it. So when C finishes up that work, which usually happens pretty quickly, it sends back a response to B. B finishes up its work, and it finishes up its work and it sends back a response to A. And then finally, A finishes up its work and sends back a response to the client. But the thing to consider here is, kind of do a failure analysis of this kind of a flow. And, and I always say, ask what happens when something fails. And I like to emphasize the simple change in the phrasing here. Often we say, if something fails, if this breaks or if that breaks. And I like to change it to say when this breaks or when that breaks, because it's a simple change of a word, but I think it raises the emphasis on the issue that you're talking about here. So when something fails, how is the system going to react to it? So going back to this scenario, this kind of tightly coupled synchronous scenario that I've shown here, one of the worst possible failure scenarios is that B can't talk to C. It could be all kinds of different reasons, because we're in a distributed environment here, right? B's running in one place in the network, C's running in another place in the network. They're talking to each other over the network. There's all kinds of moving parts going on here. And it could be the network's broken between B and C. It could be C is down, who knows? But the issue here is that what is B going to do when C's not responding? So there's basically two possibilities. B could be built so that it has a compensating action when the primary action that it wants to perform, which is to ask C to do some work and get a response back. When it can't do that, maybe it has a compensating action. Well, I'm going to give back kind of a neutral or a general response back to my caller, back to A. The other thing, though, is that it could be that there is no good response, that if C is down, B is down. If B is down, A is down. If A is down, you got unhappy users. You're getting the infamous something went wrong, please try again later, which is, getting to the point where it is totally unacceptable these days. You know, that applications should never ever do this, because you're just disappointing your users. You know, this is especially when you have humans that are interacting with your system. Here's another quick scenario of the same type of situation where, say, we have a customer service, and this is the go-to place to get customer information. So I've got this service in the middle here with the C on it for customer, and all these other services around it that need customer information to do their job. So no problem, right? There's a lot of great tools and a lot of easy ways to implement this and just make a, you know, the synchronous RESTful call from the caller services to the customer service. Customer service, you know, sends back the response and everything's good. But what happens when C breaks? Well, it could be that the failure cascades from C to all these other services. And, you know, the affected area of the application could be fairly broad in situations like this, where you have a strategically important service that goes down and affects many other services. So that's a form of tight coupling. So the alternative is a form of loose coupling. So the switch here is that often it's fundamentally just switching from using approaches that are synchronous communication to some form of approach that's asynchronous communication. So running the same scenario again, say with the customer service, where I've got the customer service over there on the right, but now we've introduced some kind of a message bus, Kafka or PubSub, Google PubSub, or, you know, whatever favorite message bus you want to use. The main thing is that we're doing some form of communication asynchronously, and this is why I asked you to be open-minded, because this is a big change here. Because the change is that instead of everybody reaching out to C every time they need data, like the customer data, the alternate flow is that every time customer data changes, C just publishes those changes to some topic in this message bus. All the other services that need customer data are consumers of those changes. And what these other services are doing are keeping their own view or cache or whatever you want to call it, but, you know, they have their own say persistent view, materialized view of customer just for each of their own uses. Now you look at this pattern and go, wow, okay, wow, we're replicating data, we're using more space, and I know there's all kinds of, maybe for many of you, there's all kinds of alarms going off in your brain going, oh, no, we can never do this. But this is definitely getting to be a pattern that is gaining some traction. And the reason for it is that when C goes down, nobody cares in this kind of a scenario, because all the other services are loosely coupled. They're self-contained. Everything, almost as much as possible, everything that a service needs in order to do its work, it can do it and respond, especially to humans, it can do it on its own with little or no dependencies on anything else. That's kind of the goal here. But we still have a microlith. You know, say you're doing things like that. You have loosely, you know, implemented loose coupling between your microservices, and things are really looking good there. But you still got that monolithic database. So in effect, you still have a bit of a microlith. And part of the challenge with this is that, say you and I are working on one of these microservices, and we want to modify the schema that our microservice uses. But in order to do that, because the schema is shared by many other components, you know, many other services, say, or maybe even an unknown number of services. So you and I have to find who else would be affected by this change that we're proposing. Then we have to talk to them. We have to negotiate with them. We have to convince them that that this change is worthwhile. And even worse, and I've run into this many times myself in the past, we have to negotiate with them to get this on their plan to do whatever work they need to do to accommodate these changes and coordinate the release of, say, these changes, maybe in a group release, for example. It can get very complicated very fast, which means it's eating up time. It's slowing you down. The alternative is that if you can do this kind of have each microservice own its own schema, it owns its own data, then the scenario becomes, if you and I want to modify our schema, that schema is private to our microservice. Nobody else knows. No other service knows what our schema looks like. We don't expose the schema. The only thing other services know about our service is what our service looks like on the outside. And on the outside is things like our services API, the messages maybe our service publishes. Nobody really cares about what messages we consume. That's kind of a private thing. But there's just kind of this external outside view or perspective of services, and there's this internal view. And I like this use of switching between, when you're talking about your service to everybody else, you're talking about the outside of the service. When you're talking, say you and I, about the service, we're talking about the inside of the service. So this is, this loose coupling then comes in not only at the code level, but it can, you can get some of this loose coupling at the data level as well. So the idea is that each microservice, I'm not showing it as a black box, but they are these self-contained boxes that that people only see what the box looks like on the outside. Nobody should see what the box looks like on the inside. Of course, on the inside, the box contains the code and data, but on the outside, you've got that nice outside perspective, and it gives you things like not only helping with, say, the development process, but even in production. If you have a monolithic database, if something else, some other service gets really busy and starts hammering the database, that can be felt by other services. If you have some kind of separation between the services at the code level, at the data level, in a production environment, maybe other services won't feel the heightened activity somewhere else in the system. They'll still continue to perform well without being dragged down. So the last thing I want to cover is event-oriented. And the idea here is that with event-oriented, and I'll cover this again, but I want to just start to bring it up, is the idea is that have a service where the service does the least amount of work while someone or something is waiting. And really someone, if you have humans that are waiting, when they ask you to perform some kind of an operation, the human device sends in some kind of a request to a service, have the service do the least amount of work as possible so that it can get back to the user as quickly as possible and push as much work as possible out of band. And this is why I like this pattern, this event-oriented pattern. So let's take a look at this. So with this event-oriented pattern, what I've arranged here in this little diagram is, so you got a bunch of clients and they're feeding in a series of what are called commands. So the commands could be things like, say this is a shopping cart app. So we're adding items to a shopping cart, add item 1, add item 2, change the quantity of the item item 1, add item 3, remove item 2, push the buy button. So each one of these things is a command being sent into the service, and there's some kind of command handler. The microservice is processing these commands, and each command is a request to perform an action that hasn't happened yet. So the command comes in like add item to cart. The service gets it. It does validation. Does this request look okay? It executes whatever business logic is necessary. And then if everything's good, then what the service does, it emits events. And so the persistence operation, which is a persistent operation, just submitting events, the events are stored in some kind of a database. But these events are very simple, and it's an insert-only operation. And by very simple, these event stores, as they're called, or event logs or event journals, they all mean the same thing, but you might hear the different terms. The database structure is very simple. It's like a key value store, very few indexes, no deletes, no updates. It's just it's just inserts. So part of the rationale for this is that it's comparatively very fast in terms of capturing new data. So the microservice is consuming these commands, processing them, and pushing events out to the event store as quickly as possible. And then the events actually are the history that aggregate up to the current state of the thing, the entity. So in the case of a shopping cart, the entity is what does a shopping cart look like? Well, the shopping cart has 2 items in it. one item has quantity 1, one item has quantity 2, and they've, the customer has submitted this shopping cart for purchase. There's all those events, including the events like remove item 2 from the shopping cart. It's still there, which is great data for downstream analytics. So this is one part of CQRS, Command Query Responsibility Segregation. It's the command part of the two parts. There's commands and queries, and the separation, the responsibility for performing commands, the responsibility for processing commands to be, the events produced by commands to be queryable are two separated things. So how does the other half work here? So this is the other part of this diagram that I want to zoom into. So the general idea is that you have some kind of event handlers that are as quickly as possible consuming the events as they're being captured by the commands being processed into events. And they're doing various operations with them. So I gave 3 examples here. So one event handler is pushing events into some kind of a message bus. So it's a very reliable form of communication. So for example, say there's an issue where this service for some reason can't talk to the message bus. Maybe the network's broken between the service and the message bus. And so what? The service keeps running. The service keeps accumulating events, new events from new commands. It runs interrupted. The service isn't broken because it can't talk to something like Kafka. And once the communication is restored from the service to the message bus, then these events handlers can pick up where they left off and catch up. Try and run as fast as possible to catch up with all the backlog of events that have accumulated while there was an outage. Same very basic processing flow exists between handling events, and then this is the query side of CQRS, where you're taking those events and you're projecting them into some kind of materialized view. And there's quite a bit of flexibility here because you could, for example, use different database technologies to support the different kinds of queries that you want to do. Maybe some of your queries you want to do in a relational database, but some of your queries you'd like to do maybe in something like Elasticsearch or whatever other database. So you're not limited here. You could have other one event handler for your SQL queries, another event handler for your document-oriented, inverted index, Elasticsearch kind of queries, and so on. And then in this example here, I have a third event handler that's pushing, say, something out to some external service. But these are all happening out of band. The users aren't waiting for these operations to happen. This is something that's happening internally in the service effectively, and it's not slowing down the user interaction with the service. So just to wrap up, there's kind of these, they're not rules. I don't want to say these are rules. They're kind of goals or things that you should try to do, think about, open your mind up to. So as I've said, implement loosely coupled microservices using asynchronous messaging as much as possible. And do something like this, make asynchronous messaging the norm and synchronous messaging the exception. So I'm not saying exclude anybody that proposes that they have to do a synchronous messaging, but challenge them. Do you really have to do synchronous messaging? Couldn't you do something using asynchronous messaging? But always have that fallback that, they got a good reason for it, go ahead, use synchronous messaging. Another goal is to try and have where each microservice owns its own schema. Turn those data references, like I showed you with the customer example, in data reference sources, turn those into publishers, and then have flip the whole thing around where the services consume changes which are stored in a way that is optimal for performance. And then another one is event-oriented is definitely getting more traction these days. A few years back, it was much less, but it's still, I think, picking up speed. So it's the same thing. Try and make, when you're looking at the design of new services, try and make event-oriented the norm, and the traditional CRUD-like way of doing things, which we all know, and love, and works really well, and everything like that. They're not a bad thing. It's just trying to force yourself to try something differently. And then always do that when this breaks kind of analysis. try hard to uncover brittle patterns. This is really important when you're building distributed systems like an application built that's composed of multiple microservices. So it's just rules of thumb. So I just want to wrap up with this quote that I really like from Carl Sagan. Many of you may have heard of him. He's no longer with us, but he was a well-known astronomer and scientist. And I love this quote. I'm not going to read the whole thing, but the parts I've highlighted, and I think this applies, he said, for science, but I think it certainly applies to us in, like in computer science, that we need to be open to new ideas, but we also need to be ruthlessly skeptical and scrutinize all ideas, both old and new. So what I like about that is it makes you look at the way we have been doing things and really scrutinize those. Should we keep doing the things that we've been doing in the old ways? In many cases, yeah, that's fine, because they're battle tested and we've got a lot of experience with it. But things are moving so fast, and there's so many great new things, like hopefully some of the things I've shown you here, that are coming up, that you have to be open to these new things or you're going to fall behind. So that's it. Just one little plug. If you're interested in these kind of patterns, you'd like to see a platform where these patterns are definitely a fundamental part of it. We've at Lightband, we just introduced what's called Akka Serverless, and it's in open beta through the summer and into the fall. You can just search for Akka Serverless, and I'm sure you'll find your way to the site that you can register and give it a try. And it's a really interesting way to do these things in a serverless way. So thank you for your time, and I really appreciate getting the opportunity to talk to you.
Thank you very much, Hugh. It was a great presentation and always great content from you. Thank you very much for joining us.
My pleasure.
For the questions from our audience. As I see, we have no questions so far. Okay. Okay, wait just maybe a second. And okay, so if any question, because we have slight delay, so if any questions occur, we will contact you and send the questions through the email to Hugh. Thank you very much for your time. Have a good day. And
thank you.
Thank you.
All right. Bye-bye.
Bye-bye, Hugh. And we are moving to another speaker that I would like to introduce. Waiting for Tim. I would like to introduce Tim Pigeon, CEO of Optrack, and he will be talking about journey from desktop to the cloud. It's very interesting. Hello, Tim.
Hello, can you hear me?
Yes, we can hear you.
Okay, start sharing.
Yes, please share your screen and we can start your presentation.
I think that one. Yep.
Yes, yes, it's working. Yeah.
Okay, hello everybody. So slight departure from the talks so far. I'm not really going to be telling you what you might do or perhaps you ought to do. I'm going to actually be talking about what we have done. In the original thing, it was described as a journey because we haven't got to the end yet. So there are going to be certain things where we have loose ends. But I hope it'll be interesting. We certainly seem to have done some of those things on various people's lists, which is good. So let's get started. So who am I? Co-founder and managing director of Optrack. These days, though, I would probably say I'm best described as being the domain expert, the project architect, and one of the programmers. I've thankfully delegated most of the commercial activities to somebody else, which is great from my point of view. Okay, so technical background, been in the business a little while, starting over on the left with punch cards and Fortran 77. If you're aficionados of old computers, that second one is an Apple IIe, I believe. IBM PCs, Microsoft Windows 3.1, Windows NT, and in that we've mainly progressed in languages through Fortran, Pascal, C, C++, and Java. However, more recently, I think that my programming history is best described by T-shirts. These are conferences that I've attended in the last few years, starting with, I think, a Scala Exchange in 2014, and most recently, Functional Scala with Cyverge and Scalac. There you go. So what do we do? Essentially, we provide an application for vehicle routing and scheduling. And what that means is that over on the left, we have a bunch of orders, and over on the right, we have a bunch of trips. Our software is creating trips out of orders in order that we can send trucks out, and they will, well, not us personally, our customers can send their trucks out and they will fulfill all the requirements of getting those orders there on time. So academically, this is known as the vehicle routing problem, or VRP. It's actually one of the most studied areas of operational research, with literally hundreds of papers published per year, and conferences attract more than 200 researchers, 5 streams, and that sort of thing. It's an NP complete problem, as you probably would have guessed, given that we have to solve traveling salesman problems within it many, many times. We're actually solving something called the rich VRP, which is basically real world problems. Academics like to keep it simple, but real world isn't. So we have to deal with things like mixed vehicle fleets, different sized trucks, complex interrelations between data elements. So for example, we can't go to one customer with a certain vehicle because it won't fit, or it has the wrong livery or something like that. We have to stack things and pack things into the vehicle, or deal with things like bulk tankers with different compartments and product compatibility issues and all sorts of things like that. Driver shift availability and brake regulations, customer time windows, and time-dependent travel speeds. So the system has to understand about rush hours when producing plans. So that's kind of what the system is doing. So our archetypal user is an ex-truck driver, probably middle-aged, has basic email and word processing skills and spreadsheets, almost certainly no formal IT training, and at best a vague understanding of files and directories or anything like that. So those are the kind of people that are actually using the system mostly. And the archetypal customer environment, the customers tend to be SMEs or local operating units of large companies, by which I mean a depot or a couple of depots working together on a national problem. Internal IT support, if it exists, is typically 24 hours away. So if you say you ask your IT support people, they'll not be able to work for the rest of the day on your data. And even when you get them, they're usually not very good or very helpful. So it's usually down to us to get the end user up and running, whether it's our problem or their problem. So the starting point for this is Optrack 4 version 1.0, which we launched in 2003. So this was a Java desktop application. It uses a Swing GUI, if you're familiar with that sort of thing. And we used to say what you need is a fast, well-equipped PC with a high-resolution screen, by which we meant probably something like, I can't remember, 1600 by 900. Does that sound like a likely resolution? 32-bit Windows, and we distribute it all by CD. So the main components in this system really are data management, which is looking after the customer's data that they give us to plan. Mapping, we have to do quite a lot of things with maps. As you can imagine, we have to calculate all those times and distances, we have to display them, we have to display a GUI layer with maps and things. So general GUI facilities and an optimization component, which actually solves the problem, and also an in-memory calculation model. And the purpose of that is so that if users make a change, we can quickly work out the validity of that change. So on data management, we don't actually own the data. So the data, the customer data and the orders typically come in from an ERP system. Usually the customers don't change so much in our system. If they do, it's only a temporary override or something like that, or fixing a wrong address. But basically the ERP is the point of truth for the customer data. And the results of the plans usually go back to the ERP or warehouse management system, WMS. Drivers and vehicles, the other main data components, come from different systems, but it's often just spreadsheets. So that data is kind of what constitutes a plan. So customers, orders, the trips we've produced, driver and vehicle data. We need to store and retrieve previous plans to recover from failure or look to see what happened yesterday, but we are not, as I say, the main point of ownership of any of this stuff. It's just a temporary sort of thing. Back in 2003, our data management was SQL Server with normalized tables, SQL Server Desktop. I don't know if people remember that. We use transactions to checkpoint user changes. And we had XML serialization to send people data sets or copy them around or back them up or whatever. And we talk to ERPs through JDBC staging databases or flat files, CSV files, spreadsheets, that sort of thing. JDBC is obviously much more reliable and structured, but we couldn't always get that. So in 2003, the maps, so what the maps do is they calculate times and distances between all customers and their nearest 50 neighbors or so. You typically, if you've got customers in the south of the country and the far north of the country, it's unlikely that any vehicle will be driving from one of those to the other one. So we don't need to know about that. Maps also provide backdrops for visualization. The sort of things that are concerned there. Street level mapping was just becoming available in 2003, but outside of the UK, it was too expensive. Navtec data sets, these things have all changed significantly over the years. Drive times were based on road types. So what sort of highway is it? Is it within an urban area? Okay, we're going to estimate the speed to be X. If we wanted to do rush hours, we'd just say 10% slower between 8 and 9. That was all we had the information for. And the map data would fit on a CD, which was nice. There weren't any libraries, so we had to code the whole lot ourselves. So all that data and so forth was done by us. And that's the GUI. That's actually the same 2.4 version of OpTrack 4, but it's still what our customers can be using. So it's a pretty complex GUI. It's got lots of windows. There's lots of drag and drop. People want to drag something from the one table onto the map and so forth. Java Swing was already pretty capable back then. So that's actually quite nice for writing these things. But we had to do them all because the third-party components weren't there. The other thing you might notice is it's using what at the time was called the MDI multi-document interface, which was a floating Windows design, which was fashionable then and is not anymore. People like docking windows like your favorite code editor or whatever. Optimization was single-threaded, and there was a limited amount of memory available to actually carry it out. Limited execution time. Users want answers in less than 10 minutes. So you press a button saying, produce me some routes. 10 minutes is the longest they'll wait. And the complexity of the problems meant we could only use simple heuristics to get, with that limited PC power, that was all we could get. I said we had an in-memory calculation model, the final element. So all the data elements are tightly coupled for rapid calculation. So if I drag an order into a trip, I need to adjust the internal data structures, check all the rules, calculate the full schedule for the vehicle, and possibly reevaluate a 3D loading pattern, update all the graphical components, and then persist the changes all in less than a second. So that's kind of the responsiveness we need out of the system. But we had evolutionary pressures. We have evolutionary pressures. It was expensive to support, partly because it's a complex application sitting in a customer's warehouse. More detailed mapping was coming along, more complex problems, and we were getting competition from simple and, at the time, quite simplistic cloud-based solutions. But because they were easy to deploy, we were losing out. So that's. So just to have a look, can you just give me half a second, because I realise that I don't have a clock in front of me. And no, I want a clock, sorry. I don't want to overrun or anything. Sorry about this. Right, okay, I know where I am. Right, so often we are the only lifeline to the end user. So if something goes wrong, he's got 20 trucks that need to go out first thing in the morning, and nobody else but us to help him sort that problem out. Most of the problems are due to external factors, like bad input data. Somebody's created an order with a 0 volume and they're wondering why it's called, or it's 1,000 tons per unit, and they wonder why it doesn't go on any trips. So we have to diagnose and provide workarounds for the user, but that depends on us getting hold of their data so we can figure out what's going on. So a real pain point was actually getting the customer to give us data. So they're sitting there in a depot with all their data on a PC, and you're going to say, can you send it to us? So yes, file manager, little yellow icon, click on that. There's a directory, scroll down, etc., etc. There was quite a lot of challenge in actually getting customers to give us their data with their level of expertise and knowledge. So another pressure, more detailed map. So affordable truck-aware street-level maps have been becoming available and were available in all our target markets by 2015. So as an example of how much data there is, the UK has 50 million road links. The USA has more than 6 million. The USA has more than 50 million road links. And the data sets and in-memory representations for this are multi-gigabyte. And we can't buy third-party services that do everything we need. Still can't. So the first thing then we looked at was to try and give ourselves something of a solution on the maps. So we delegated our rendering to an open source Mapnik service, which is the same thing you can see on OpenStreetMap. So that's actually now drawing the maps from a database. That's nice. And we can run that as a service. Then we can extract from the desktop all the map calculations and put those onto a server. That server then gets an HTTP-based API, and we can implement multiple map services with some sort of Azure Failover service. So this is microservice number one. We've managed to extract the maps out of our application and put them on services. So this allows us, this is basically the only way to deal with those big maps. We can control the map updates, we can ensure customers using up-to-date mapping, and we don't have to shuffle large amounts of data around to customers and so forth. And we can use multi-threaded services in our servers, so we can do faster or simultaneous calculations. So that's microservice number one. There are problems with this. Java's not an ideal language, and it uses mapping routing algorithms from around about 2000 in our old code. And there have been lots of advantages since. And we also used a nasty homebrew service discovery thing. So that was our first service. So moving to the cloud more generally then, what we want to do is, can you just bear with me? I think I've missed I think we've missed a section out. Yeah, sorry. I think I skipped over this one by accident. So the other thing was the data. So getting rid of that local SQL data store, we were able to replace that with a blob store, and then we were able to use Azure as a blob storage as our primary repository of the data. So we've now put data management, instead of being our problem, is now Azure's problem. And the systems, providing they have a decent network connection, can put that data there. And the real impact on that was that on support, we no longer have to talk to the customer about getting hold of their data. Instead, we just say, which data set are you using? Okay, exit the system. That's unfortunate. Our system is currently still single user. And then we just open our data set in our own environment. We still have to diagnose the problem, but we've eliminated that pain point of getting data off a desktop in a warehouse somewhere. And now we can just get at it with a few clicks in a couple of minutes. And we can then look straight at the data. Sorry, this one. So the targets are moving to the cloud. As I said, the existing system is desktop. Obviously, it's going to be single user. Well, not obviously, but it is single user. We want multi-user access. We want easier integration with real-time vehicle and driver tracking. So this is where we are knowing that a parcel has been delivered, the vehicle is at this location, stuck in a traffic jam. We wanted zero deployment, and we wanted easier integration with the web-based ERP systems such as Microsoft Nav. Well, it keeps changing its name, it's something else now, NetSuite and so on. We want to be able to take advantage of the latest optimization algorithms, not algorithmics, and we wanted to be able to use the latest map algorithms, which are also considerably advanced. So as a general approach, we wanted to give ourselves maximum bang for the buck from a small development team. When I say small, it's 6 people. That's it. That've got to do all this stuff. So one of the ways to do that is by using the best available open source. We need to make development fun, or at least interesting, because it's a small team and we can't afford to lose anybody. We want them to stay, and that seems to be a good way. We're using Agile and something approximating test-driven development, continuous integration, and so on. So our final stack, this is final as of, we haven't finished yet, but this is what we expect it to be, is Zio on Scala, Rust for the maps, Vue for the GUI, Kubernetes, Kafka, Postgres with PostGIS, Weka for some machine learning stuff, and we're currently sending our information around on HTTPS, I should say, and WebSockets. So how's that all impacted us? So
we have some temporary problem with the connection with team. We are working on this. We are trying to figure out what happened and get back to you shortly. Okay, so unfortunately we lost connection with Tim, so I guess that we cannot continue his talk. I guess that we can record something and deliver the full talk later after the conference. Sorry about that. So the next talk will be in 7 minutes. Marek Rygielski from IBM. So grab some drinks, snacks, and see you in a couple of minutes. Hello and welcome. We are going to start our next session with Mary Grigleski, developer advocate from IBM. Hello, Mary.
Hello, Thomas. So good to see you.
Yes, yes, yourself. So Mary will be talking about a very interesting question. I'll be trying to answer a very interesting question that we also received before the conference. Is microservices the silver bullet? So should we use it everywhere? So Mary, handing over to you. Could you please share your screen and we can start your presentation?
Yeah, sure. Hold on a second. It's been a bit of a crazy thing with my machine, but I'm sharing my screen now. So, okay.
Yes.
Okay, share screen. Somehow I think because I'm having issues with my computer, so it needs my security set up. So give me a second. I'm so sorry.
Yeah, no worries. Okay.
All these things. And then it needs my password. I am very sorry. It's kind of amazing, right? We're doing so many things all the time. Wait. And then if something doesn't go right, and then that's what happens. So I just have to give permission, and will not be able to record. Okay. Oh wait, it needs me to exit this and then comes back. And so if you don't mind, I'm going to quickly exit and then come back. I have to basically close the Chrome and then come back.
Sure. Yeah, okay. No worries,
okay.
Mary. We'll be waiting for you.
Okay, thank you.
Yeah,
sure. For a few seconds. Okay. All right.
So we are waiting for Mary to reboot the computer, and we will start our last talk for today, planned for today. Just one remark: if you would like to ask any question to Mary or to any other speakers that presented before, please use your chat screen on the YouTube channel, and we will ask these questions after Mary's presentation. Also, if you would like to ask any questions after the presentation, just drop us a message at info@scalac.io, or you can find us on Twitter, and we can handle any questions. And also, if there will be need any help from Mary, we can follow up with Mary. So, are we ready to start? Yes.
Finally.
Okay.
Got things set up.
Your presentation.
Good things come at last. So I promise a good show. So thank you. Thanks for your patience. So.
Yeah. No worries. It's always a pleasure to have you, and especially to see your presentation. Yeah. So handing over to you, Mary.
Thank you, Thomas. Thank you, everybody. Welcome to my talk. Again, thank you so much for your patience with me. There's been having some machine issue and all kinds of stuff. But so thank you. Right now, we're almost summertime here too in Chicago, and that's where I'm based at. So lots of things happening, and I'm sure too it's beautiful in Poland. I wanted to come, so when I can travel, I would definitely visit. So, okay, but back to serious business. We're here today. My talk is about really questioning, right? Is microservices the silver bullet? Is it a cure-all? Does it solve all the problems? It's got some noble ideas in here. So I'm gonna explore this topic, right, within the next 25 minutes or so. And okay, give me some patience. Let me kind of advance my screen. First of all, who am I? Who is Mary Grigleski? I have a Polish name, actually, as you all know. It's because of family. And anyway, but I love it. And so I'm familiar, with a lot of things in Poland. And I just, like I said, I love visiting your country. Anyway, so I'm a developer advocate, senior developer advocate at IBM, primarily in the Java, open source, cloud, and DevOps space. That's what I do. And also, too, I have heavy interest in enterprise distributed systems. So that's my area. focus. And currently I'm with the WebSphere engineering team. So my project areas are all open source Java related products, OpenLiberty, MicroProfile, and Jakarta EE that are perfect for doing microservices development in the cloud native time period that we are in. And outside of work too, I'm also very active with the technical community. I'm a president of the Chicago Java Users Group. We are 3,100 and more members these days. We're running online meetups in the pandemic time. So if you'd like to join, please, by all means, join us too. And I have over 25 years of software engineering and architecture experience in various capacities, product development, and also applications too. So I've done applications in the enterprise world. So I kind of bring a unique perspective too. I've done product, which is kind of slightly different than applications. You're really in the trenches, so to speak, right? And helping to deliver software. So I fully understand, right, the challenges that's kind of we face every day. So, okay, so with that, let me start. First of all, let's ask too, and I'm sure you already have heard of microservices, but let me kind of make sure we're all on the same page. So what is microservices? So I kind of look up, right? Everybody look up at Wikipedia. It's essentially, right, it's an architectural style. It's a variant of the service-oriented architecture, SOA, structural style. It arranges an application as a collection of loosely coupled services. So that's like the core of it, is a loosely coupled thing. And in microservices architecture too, services are very fine-grained and the protocols are lightweight. Excuse me. So it's essentially too, if you look at this picture, right, it's like all of these, specific service, right? That's what it is. It's basically usually, right, we use RESTful kind of exposure for connection. So in this case too, they are independent. They have their own database. They manage their own resources. Everything's very independent. So that's why I highlighted the loosely coupled kind of aspect of microservices. But let's kind of get into a bit of history behind microservices. As some of you too may have kind of worked through, right, through history, how did we arrive at where we are today with microservices? So before there were microservices, there were SOA, service-oriented architecture. And then also enterprise service bus, the ESB. So ESB isn't necessarily the only way of doing service-oriented architecture. You can have others, but the thing is, the primary kind of driver of that was actually the enterprise service bus. So I myself actually have worked on the Oracle Enterprise Service Bus ESB for their Oracle Service Bus product OSB. So I'm familiar too with SOA, and I can also understand the pain too of SOA. It's not so much like it's bad. It's just that it cannot like grow, with the times, with today's world, cloud native kind of era, right? So that's where we are in. Okay, so before SOA, then what was it? It was actually monolith, right? Everybody's heard of the word monolith, and I specifically use a dinosaur to indicate that, right? But it's sort of more like, okay, everything's as encapsulated into like one like giant kind of a service, right? Now, for me, I come from Java background, so it's more like the VM, the virtual machine, that kind of essentially encapsulate all of the services within the same JVM. So there are obviously like, challenges too. So let's take a look. Challenges of the monolith. Large code base, right? We tend to have many business modules, especially for like serious, like enterprise computer systems. So say, for example, I worked at the Chicago Mercantile Exchange. So as you know, right, futures, options, financial exchanges are very hard, fast-paced, and a lot of information, all the trade information, trade subscribers, traders, and all that. So the thing is that we have like separate, systems, right, for employee, and then there are customers, there are subscribers, there are partners, there are like little trading firms that partnering with that, all these things, right? So a huge code base to manage just the resources, people aspect, companies and entities, and not only that, then the trading aspect, and not only that, right, on top of that, regulatory, all these like important things to kind of keep the exchange running. All these things is huge. The code base was actually very huge. And in fact, there were like separate systems for even doing clearing, right? To clear all the trades. And it almost seems like a separate company. So all these things, right? It's huge. If you do everything monolith, then guess what? I'm sure we all play the game three-legged race, right? And when you have to like partner with someone, you tie your legs together and then you try to run, right? So I kind of think of monoliths. If you every time you do any kind of upgrades or just small updates, you have to make sure everybody is in sync before you can do anything. So that's kind of like a challenges of that. However, think of the good things though, as compared with today's microservices, is that like if you have everything all together, well, guess what? From a programming perspective, in some ways it's less kind of complicated in the sense that because you do not need to necessarily communicate with another process outside of it, right? There's not much to worry about the network, the latency, that kind of aspect. So there's some pluses too, but then the times have changed. We're in a cloud native era. Everything has to be fast and quick. Containers, all these things. So the monolith really cannot handle the pace that are going. So okay, so if you think of it, right, even like deployment aspect, right? I remember myself, right, doing deployment. Oh my, you need to deploy the order. Let's say the order aspect, right? You essentially have to have all of the other components all like wait, in a wait state and stop because they have so much like tightly coupled dependencies. The integration, kind of like interface are like, not very clear. Everything is really tied together. Think of it like Lego's pieces. Instead of Lego, you get the pieces all glued together. So it's very hard. You want to deploy, it's hard, And then if we're doing work myself in development and all of a sudden QA says, well, it doesn't work, they report problems, and your development wants to replicate, kind of they reproduce the error using the same environment is close to almost impossible sometimes. And then if you want to do it, it will take, a lot of, time to do that. So it's very expensive, right? And so now if you think about it, right, there's also scalability aspect, right? Systems grows, you need to have more customers now, all that stuff. You want to scale it is also a nightmare. You want, all the intermodule dependencies, I already talked about upgraded hard. So now then let's move on, right, to SOA. SOA benefits is really like over the monolith is really the reusability. It encourages reusability. And I also talk about, right, the enterprise service bus. So you have like a single kind of communication kind of a channel that channels all these services and services, all of them. So it seems like good, right? And then there's also stateless services, right? You can use HTTP, all that stuff. It's quicker. No doubt it's quicker and everything. And there's interoperability too. In fact, SOA kind of works quite well in the sense that you can use different protocols. Now, if you have worked with it, that's the web services description language, where you kind of describe all of your interface very clearly. So you can also have different toolings, different languages to implement different parts of your system. At different, clients, you can have like a JavaScript client talking to an Oracle, enterprise Oracle, service bus SOA using SOAP, right? And then the simple object, simple object access protocol, right? So SOAP protocol actually is over as HTTP, all these things. And then you can, again, the WSDL, right? WSDL, the web services definition language, contract based, and it just all seems good, right? And you can scale it. Okay, that's okay. We can scale it too. We can handle it too, right? If you're like running Oracle at the time I did, was like you kind of just follow the instruction, do all the clustering, the load balancing, all that. Yeah, so life seemed to be good for a while. And you try to upgrade, you can upgrade easily. But it falls short, on the communication. You're depending on the ESB, right? The single point of failure. If that fails, everything fails. And service granularity too. You can range, the services too. You can certainly kind of do it like the microservices style. Nothing's stopping you. Small things, small services and all that. But then there's sometimes though, in a complicated enterprise environment, you have complicated things to deal with, right? So just your services can also be very big. And I recall some of these, right? Especially when you're dealing with some sort of like order processing. It gets quite complicated, right? And has to link into shipping, link into, well, not only that, before that, payment and all those things. It gets kind of complicated. It's less granular. And the speed too. Actually, the thing is too, they operates slower too, because it favors, right, the starting of resources. Now, that's the thing with SOA, you share all the resources. You have maybe like 1 or 2 copies. I mean, the database itself can be replicated, but each one, well, kind of, I should say, all the services access the same database essentially. So the thing is, it can be slower. You can have bottleneck, right? If you don't have enough connection pools and things like that, if you don't tune it right, it's got issue. And also too, let's then kind of move on to microservices today, to today's world, but some historical tidbits, right? So the term microservices was kind of first kind of used, it was back in the mid 2011 at a workshop of software architects. And from ThoughtWorks, we have James Lewis, the architect leader, and he presented the first talk about his idea about microservices back in 2012 in March. And by the end of 2013, that generated enough interest, right, in the whole IT industry that they start talking about microservices. So what it is, right? So finally, in 2014, Martin Fowler, the kind of leading expert, right, from ThoughtWorks, with James Lewis, they both did their first talk, like official. So essentially, microservices architectural style is an approach to developing a single application as a suite of small services, right? Each running in its own process and communicating with lightweight mechanism, often HTTP resources API. And these services are built around business capabilities and independently deployable by fully automated deployment machinery. There's a bare minimum of centralized management, and that's kind of like the key. There's not centralized of these services, right? So supposedly make it easier if you're decentralized. And you can write that in different languages and different flavors of things. So essentially, it doesn't dictate what you need to use to implement it. It's just a style that you must follow. So all is good. Now, in today's world, cloud native and microservices. Okay, a match made in heaven. It sounds like good, right? So let's take a look, right? I'm gonna kind of describe a bit of cloud native, especially if you are still contemplating about doing things in a cloud native way. But I'm guessing a lot of maybe companies are already considering or already doing it too, maybe quite advanced too. But still, this is an area that's kind of growing. Is essentially cloud native is an extension. To me, in my mind, I think of it more extending the cloud computing capability. Because in the 2010s, right, when cloud first came out, it was mostly about cloud infrastructure, Kubernetes, containers, all of these. They do their work well, but they never really get themselves into application. But the thing is, though, in all kinds of business, the application is the key, right? It is the main kind of driving kind of important things to keep your business running, keep the world running, everything. So that's actually very important. So cloud native is essentially you leverage on the cloud computing infrastructure and extending the cloud for enterprise, especially for the enterprise business operational type of systems, highly distributed like that. So, okay, so then let's take a look, right? How do we do cloud native development? It's essentially also cloud native is like an overarching approach to it, covers everything. If you think about it, it covers like development in the cloud infrastructure, which means like everything. Okay, so I kind of quickly kind of copy over these 12 factors. There have been also talks about 15 factors now. There are additional factors, but Heroku, right, the company that they do also they host systems too, right? They host like cloud systems, cloud native systems. So they come up, right? The developers came up with this 12 factor. It's a guidelines for doing cloud native. So as you can see, I won't go over every single thing, but just pointing out too, right? From the code base, right? You must have your code in the code base that are versioned and everything, so you can kind of go back and trace back if there's something goes wrong, you need to roll back. And then there are also like dependencies. When we run systems, it's not just the system itself. There are lots of inner workings, so it manages all of these things, configurations. The backing services, logging. Okay, so one important aspect, DevOps, right? DevOps, it helps with actually enabling the whole cloud native the systems to be very efficient, right? The code comes in, you want to do an quick like continuous build, continuous integration, and then as a result, continuous integration and then deployment, right? Make it ready right away. So the whole cycle is real fast. So I highlighted to number 6, it specifies processes, right? Processes basically is you want to execute the app as one or more stateless processes. So stateless is the key. Stateless is there's no need for you to worry about keeping track of the data. Everything you do, just do it. Think of something like no memory, just go do it. Very agile. So that actually microservices architecture fits very well into the cloud native kind of specification, or kind of like the guidelines. So now if you continue looking, there are also port binding, the concurrency, all these things, but there's also the disposability. It means that you want to make sure that your service can not only, can execute, but it starts up fast and also has graceful, quick shutdown. So that also microservices conforms to the standard kind of specification in the guidelines in this 12 factor. So as you can see, microservices and cloud natives are kind of perfect, right? And then there are other aspects to the logging, the admin, all these things. You want to essentially decouple all of these different kind of aspects of your whole system. So it covers everything. Okay, so now then kind of comes into question, right? Back to my original question of this talk is microservices the silver bullet? And the answer is that it really isn't. It isn't a cure all kind of solution. Now, but that's the thing, is not like to say, okay, don't do it. That's not what I meant. It's more like, let's examine what it really is, get a really good understanding, and basically use the right tools, the right approach for the right job. I think that's the attitude we should always have, right? It's not just like, okay, it's hot, let's do it. But it's more like, well, let's see what we have. We go and examine our business processes, what it is, and what is it that we're doing. Are we like into e-commerce, right? Or dealing with other things. For example, like telescope. I'm involved with a project actually doing telescope, right? Kind of astronomy, kind of collecting data, right? IoT and all that. So they're different tools for different purposes. So we need to always like look at our business processes and take a look and see if it's, are we using the right tool for the right job? So, okay, but back to microservices. So the idea is that this loosely coupled decentralization. So the question is it really so? So I'd say no. Let's go. Okay, so first of all, let's kind of consider, right? So now what used to be, right, like a one system, then we have all the components all together. It's easier and to do things, but now, breaking it up, and of course they all run in their own space. Not only that too, right, in a cloud native environment, you got services that are replicated, let's say Kubernetes, right, on the different pods. Different pods can sit on different, persistent storage, right? All of these storage, and they can be logically the same, but they are on different, physical systems. And sometimes, a lot of times too, especially if you want, with Kubernetes, it also has a lot of replication, for high availability, kind of disaster recovery. You replicate all of stuff all over the world and everything. And the thing is too, with cloud native, with Kubernetes, it keeps the state of all of your pods conforming to the spec. So at any point in time, if a pod goes down, it will generate a new pod for you, that type of stuff. So it has all these functionality. However, nothing can happen without the network, right? So now there's this kind of idea of network fallacy, right? So basically the fallacy of distributed systems is noble and grand. But we're kind of like assuming, that we're believing that the network is secure. That's one thing. And also the network kind of stays up all the time. So that's the thing, right? That's this aspect. And not to say we don't do anything. That's not what I meant. But it's more like, okay, with that in mind, then we want to make sure that in any point in time too, when you do microservices, especially in a containerized kind of approach, especially in a cloud environment, you get charged, by the minute, by the seconds, right? Sometimes. And so the thing is too, you also want to make sure that your microservices are very slim. There are no additional burden that's kind of you need to carry around with your microservices, very precise, basically. Because what is happening is that in the container world, you have these servers, but your servers are hosting, they're multi-tenancy, right? You're hosting many versions of or actually not versions, instances of your containerized microservices. So you want to make sure each one of them use just the right amount of resources. If it's not, processing anything, it needs to kind of be idle and not be charging your money. So that's very important, right? And all these things. So, okay, so back to that is that there's network latency too, right? That can also easily add up too if your number of microservices is very high. And actually, one thing I wanted to point out too And that's something that that I recently started chatting with the Java performance expert, Kirk Pepperdine. He's with Microsoft now. He's kind of the authority on Java performance too, JVM performance, right? Among the few who are very good. So he was just kind of commenting to me that they've done a research on testing microservices. And believe me, the thing is that what they have found out was that it's really the thread scheduler that is the bottleneck, right? You can kind of, a lot of times if we say that, okay, there's network issue and all these things, and we can increase memory and all those things. But the thing is that the unit of work has to be very precise too. So then you don't kind of do extra things. And so how you design your microservices is also very important. You want to make sure that the size of it is important, and there's also the thread scheduler, because every time, right, we think, oh, we're doing microservices, but underneath the hood, on the lower kind of computer kind of infrastructure layer is really the threads that are like sending out all the work to kind of say that it's your turn to execute all these things, but it's really the scheduler that's kind of controlling all of these. So you have to make sure that that's kind of like the essential kind of driving thing to kind of make things, your microservices be executing. So you do want to make sure your microservices are designed very well. And also then keep in mind, right, there's network fallacy and all these things too in mind. And so that's something I think it's very important too. So, okay, another aspect of it too, I'll be cognizant of the time, I kind of tend to like to talk. So, okay, then another thing is that there's also business transactions. So that's a talk that I recently started talking, right? So don't forget too, we are dealing with a stateful world, we're dealing with business transactions, e-commerce, right? How often do you hear to customers, they are in your e-commerce system, you're trying to order stuff, and because it's the complicated thing, right? You're doing ordering, and then at the same time, you are checking to see if your catalog inventory system has the merchandise that the customers want to buy and all those things. So all these processings are happening. They have transactions too. So you want to make sure that data consistency is very important. Let's say you want to place an order, and then you go to the next microservices, you place the order. Okay, well, the order is being put on hold. So all of the other things too will be doing their checking, checking your credit card, checking your inventory. All these things are happening. In the meantime, the order is being kind of put in, kind of like a waiting state, right? All these kind of orchestration too is very complicated, right? And the thing is, so that's another thing. In a cloud native world, right, we're talking about stateless. So, and then the question might be like, what are we talking about? We're doing containers. We mean to be fast, but our real businesses, we need to deal with real stuff that we need to maintain the state that actually goes against the principle of stateless. Now, I have another talk that talk more about how do you do stateful, right, to maintain the statefulness. So that's important to know too, not just like doing microservices. We got to take care of business. We want to make sure that especially some business transactions can span days. Maybe you are like doing some ordering, you are like putting the order on hold and things like that. So you want to make sure that there are all the facilities in your entire system be able to keep track of this transaction so that it doesn't get lost. If your server often lost power, things like that, right? You have somewhere where you can back up and make sure you save all of these transactions that are still being, kind of like in the middle, right? Kind of in a suspension, well, not just suspension state, but it's more like in a wait state, for the next transaction, next action to do. So all that kind of stuff, is not as simple as it looks, but there are obviously kind of toolings out there to help you do it too. So, okay, so that's something we need to get in mind. Now, for me too, well, because I don't have as much time, so I just want to also point out this very important thing is actually technology is important to kind of make sure it can do its job. But the cultural change too is of equal importance too in your migration towards more of a microservices, cloud native changes. You want to, because now you're breaking down, all of your operational details, implement them in different services. So then it will naturally involve the people who are working on it. There are different departments. You have order department, purchasing department, shipping department, the credit card, all these things. So you want to make sure, ultimately, to make sure everybody has to work kind of peacefully together. Now, if one my order department, the people doing that work, they're not willing to kind of work with the people in the inventory, then you'll be in trouble. And then if you kind of publish certain interfaces, right, APIs, and then if the other department said, no, we want to do things this way and that way, you end up arguing, and then, nothing will get done. So it's ultimately important too, alongside with your technology, you do need to have the organization to be ready. You need to have management supporting these changes, and also understand too, right? The developers also under big, kind of a pressure too. They are also maintaining existing systems, but they also have to take care of new things, right? So kind of make sure that these are all being addressed too, not just like doing the work. We're living in a giant, very complicated world. However, if you make this fun, right? This can be fun. You're trying to do distributed systems, and everybody doing things in a new way. I think that's what it is, right? And instill a sense of like, kind of this is like fun thing. We're making things better. It will be better in the future. I think that would be really great and make everybody work together. So. Okay, so I think my time is up. Yeah, I think I'm supposed to be only, and I started late, so I'm kind of a little bit late. But I do want to share with you some resources. It's a bit more of a technical side, but at IBM, because I'm come from a technology development, advocacy. So I'd like to just point out to you too, right? At IBM, we have microservices. If you want to learn more about it, we have solutions that we offer to you too in your suite of products that you're considering. And of course, there's also SOA that I talked about, right? We have IBM Cloud Education that also gives you information on that. And then there are also industry information. I mentioned about Martin Fowler, James Lewis from ThoughtWorks. There are links to all the microservices. And Chris Richardson, based in California, and he has great things on microservices.io, that site, design patterns. And myself too, I work with Open Liberty, MicroProfile, and Jakarta EE. These are all conforming to the Java EE spec. So if you need more information, please reach out to me. And how to reach out to me, these are like the various ways. Follow me on Twitter, my LinkedIn profile, and also my Discord server if you want to continue with the technical discussion. So, and that's all I have for today. I hope it's kind of helpful and kind of help you to, as you navigate right through this complicated maze. So yeah, thank you, Thomas. Thank you so much. Yeah.
Thank you very much, Mary. Thank you for your talk and being with us. I really appreciate this. And so thank you very much.
Thank you.
I'm checking if we have any questions to Mary.
Sure.
Maybe one question from my side, because you mentioned at the last slides about the structure, or maybe the question is, do you think that team structure is an important success factor in implementing microservices architecture?
Okay. If I understand your question, you're saying that like a thin structure, you're saying?
No, a team structure. So
team structure. Yeah.
Yeah.
That's right. Exactly. I think that's what I thought too, right? I was kind of talking about the cultural change is really inevitable. It is very true. Like I said, I also was actually in a cell phone company before, in which we were starting to break things down into microservices. So we have different teams that actually work alongside, like the development, right? We work alongside with the business functional side too. And we found it to be most kind of productive, because then we kind of get the people doing the work and then talking with the business people, the stakeholders together. So that kind of structure, it seemed to have gone well. It is my experience too. But of course, different companies have different culture. So you may want to experiment with that, and also kind of get everybody the mindset. I really kind of can't emphasize enough about the need to get everybody's mindset to be ready. There will be change, but the change is good. I think that's what I feel is very necessary, and it can be fun. And that's the kind of sense you want to create in people, and kind of rally the troops, get them excited and do things in a new way. So yeah, that's what I think. So.
Thank you, Mary.
Thank you, Thomas.
We have one question, as I see. Let me read it. So the question is ASB in software in SOA fulfilling same role as service mesh in microservices?
Oh yeah, good question too. SOA, they do too, ESB. I think from a business perspective, it does solve the business problem. However, in the cloud environment, cloud native type of newer infrastructure, right, dealing with cloud containers, I feel I haven't actually done any SOA and then deployed to the cloud. I'm not even sure, right, cloud native. But I think the thing with microservices is definitely the architecture to use if you are kind of moving to more of a cloud native way of implementing your whole infrastructure and your whole application. Because again, SOA, ESP, right? The ESP is kind of like the central bus. So you still kind of have a bit more of a kind of a tight integration between all your services have to go through the bus. And so it can be, it can be efficient, but at the same time, if the bus ESP goes down, then you're kind of in trouble, kind of thing. So yeah. And then that's my kind of opinion on that. So yeah. And somebody asked a question. I'm sorry. Yeah.
Yeah, is there any other question to Mary? No more questions. Okay. Hope to have you, Mary, on site next time in Poland.
Yes. Yeah, I would love to. Yeah.
Thank
you.
It will be possible. So so thank you very much, Mary. Mary was our last speaker. And I would like to thank you to all of our speakers. It was, I guess, a lot of stuff about microservices from different angle, from helicopter view, from security, from the startup point of view. So I guess that there will be a lot of good content to discuss. We are always happy to answer any questions that pop up even after the meeting. Just please visit Scalac.io or just send us info at send us email at the info@scalac.io. All recordings are already recorded. All talks are recorded, so you should expect that there will be available soon. On our YouTube channel. Also, please follow up us at Scalac.io, and we are trying to deliver the best content. Thank you so much to Maya and Jacek at Scalac. And so it was great to have such a great team. And so that's almost all for today. Thank you very much. See you on the next episode. And yes, we had planned one more speaker from Splunk. Unfortunately, he didn't manage to join us, but I hope that we will record this meeting and will be available on our website or YouTube channel soon. So thank you very much once more to all participants, and see you again. Bye-bye.